Good morning, everybody. I think it's time, even past time, to start. So we are very pleased to have you in Avignon for this workshop. So field phenotyping in France started a bit more than 10 years ago. At least in Avignon, we started in 2008 with our colleagues in Toulouse. For some project on wheat. And then Benoit joined us. And then we started another project which was called Breed Wheat, where we try to actually use remote sensing techniques for phenotyping. So that was partly successful, but that was a start. And then we at the same time that the project Phenome started, so in 2012 about, the CAPTE group, which is a grouping between Arvalis, let's say Applied Research Institute, and INRAE, so mostly Arvalis, started to work, so to develop tools first for phenotyping, because we didn't get at that time too much tools. And then in the second phase, so more recently, with the second phase of CAPTE and the second phase of Phenome, we were mostly focusing on, we were mostly focusing, we are mostly focusing on the development of the methods to interpret the data, because at the beginning, okay, we didn't get too much, we didn't get too much of those tools, no deep learning at that time, and also no tools to acquire data. Okay, so that's a short history of what we are. So here in the second phase, the Hyphen company that was created within the first CAPTE period joined us for the second CAPTE period, and now is well developed and is part of the development of the phenotyping techniques and the methods. Okay, so I will. So in the CAPTE, INRAE has got the role of, let's say, more research. So let's say probably less operational techniques, but trying to find new traits or new methods to reach or to derive those traits. And then the other partners, so Arvalis and Hyphen, are completing, and we are working in very close interaction to develop and improve and try to go to the scaling of those methods. So I will let the...
Yes, thank you, Fred. So I'm Benoit de Solan from Arvalis, and as Fred says, I joined in 2009 and 8 in Avignon to develop these techniques. And for us, it was, so Arvalis is an applied research institute, so it's a bit in between private companies and research institutes. So it was a good scale to and a good positioning to make R&D developments. So to push the developments a bit further than pure research, but with less constraints than purely private companies. So for us, the aim was to automatize as many as possible of the traits estimations, because a large activity of Arvalis is to collect data in the field and build references, and from these references to build tools to give advices to the farmers. So the automation of and the digitalization of phenotyping was a big issue, and especially at the French territory scale. So we have 27 research stations, so we needed systems who could be deployed at this scale. So that was our constraints, and our strength was to be able to collect data in many different situations and build data sets and reference measurements.
Yeah, and the last one in this CAPTE unit, which is really what is happening in phenotyping in Avignon, is me. So I worked with INRAE, I worked for Arvalis as PhD students, and then we founded Hyphen. Hyphen really had the objective to put all this research available to everyone, at the same time researchers and also companies. I guess that if you want to know more, please feel free to speak to me or to any other members of Hyphen that are here. There's a lot. I would like also to thank all the sponsors of CAPTE workshops. So we have, I think it's, you know them better than me.
So we thank first Avignon University who welcome us here. And we thank also the Phenome Project, which is supported by the National Research Agency. We thank also the Ministry of Agriculture and Food, who found the unit, the CAPTE unit. Also Plant Phenomics, which is a journal in which Fred is involved. We thank Digitag, who provide us, which is an institute who tried to combine different initiatives on digital developments. And we thank also the Invite Projects, who is dedicated to developing phenotyping tools. It's a European project. And I think that's already good. And also, of course, our yes, INRAE, Arvalis, and Hyphen.
Let's start. So I think we can start now. So the workshop is split in 2 sessions with dedicated topics on different type of traits. And the first one is dedicated to the structural and morphological traits. And José Berni will present us new Lidar exploitation. So, José, it's up to you.
Thank you, Fred. Well, first of all, I would like to thank the organizer for bringing me here and really congratulate them, because it's when you look at the program, it's really exciting and really impressive. And I think, especially after the COVID, seeing each other face to face after all this long time is great. So, yeah, congratulations, and really looking forward to this coming couple of days. So I'm going to talk today about some of the new exciting technologies that are coming out of Lidar and how we are using them, not just in the context of phenotyping, but also how we are trying to integrate this into crop management decisions, and how can we translate some of these phenomics approach that we're going to see over the next couple of days? How can we integrate them into agronomy as well? So for me, when I was a kid, I was really excited with lasers. I'm probably who wasn't excited with lasers and in concerts and movies. And so I really wanted to work with lasers when I was a kid. And here I am, ended working with plants, but still there's hope. And now I'm working with lasers as well. So pretty much the way that we use lasers is in LiDAR, and LiDAR stands for light detection and ranging, is we use the laser to measure the distance and the angles to the targets, to the objects. And by moving these lasers in different directions, we can create a 3D model, a 3D point cloud that represents in 3 dimensions the canopy architecture. And then we can integrate these in different ways to extract different traits. And this is what we're doing, and I'm hoping to see some more presentations in the next days of how people are using laser. But to be honest, if there's an exciting time to work with LiDAR, it's right now, mainly because of the car industry, robotics, autonomous cars and everything. There's an amazing future for LiDARs, and there's so many products coming out in the market. The reduction of the price, the specifications of these new devices is pretty amazing. So just a few years ago, to buy a LiDAR similar to the specs that you can buy these days, you will have to pay like 20,000, 50,000 euros for a single unit, and maybe more. Now you have LiDARs like this one from from Livebox that is actually commercialized by DJI that costs 700 euros. That's pretty amazing. And the same thing is happening with some other auxiliary technologies that are required for the LiDARs, like, for example, GPS units, IMU units, and things like that. So there's a few things coming out, like these multi-layer lasers that actually create an image in 3 dimensions with very high resolution, or all these solid-state LiDARs that don't have any moving parts, which make it really interesting for agricultural applications. So I'm sure that in a few years' time, we're going to see LiDARs on every car like we see GPSs these days, and probably we're going to see LiDARs on tractors and machinery like we have GPSs nowadays. So traditionally, LiDAR has been used, well, for cartography, obviously, because the interesting thing with LiDAR, being an active sensor, it doesn't rely on the light conditions, it doesn't rely on the sun like most of the remote sensing instruments that we use. And this also has the advantage that it can penetrate into the canopy. So if you're flying a forest, the LiDAR penetrates into the canopy and you can get different returns or different signals from the top of the canopy and the ground. So that makes it really useful to remove the vegetation and to get a digital elevation model of the terrain. In our case, we want the opposite. We want to get the information of the vegetation, and actually this is the part of the returns that we are normally using. And this, for example, has been used widely in forestry applications. So LiDARs, terrestrial scanner, laser terrestrial scanner mounted on a tripod, like you can see in this picture, has been used to map forest attributes, to map biomass, to count trees, to characterize the forest stands, and this has been used routinely. But obviously, this needs to be moved around. And this is now what we see in many cars, both for autonomous cars, but also for mapping, is mounting LiDARs on some moving vehicles where we can create a moving map in 3 dimensions. LiDAR has been obviously used in phenomobiles. And phenomobiles, who most of, for any of you who are not familiar with that, is a term that indicates kind of a high, a tractor on high wheels, so this allows us to move on top of some of the traditional phenotyping plots, where we can mount different instruments. And there are many examples of phenomobiles, and here Hyphen is one of the major companies manufacturing them, and the group here, I'm sure we will see some examples of phenomobiles. So basically, we can mount instruments on these devices. They can be heavier, more complicated, or easier, like this one in the video, that can be moved manually. And basically, you integrate different instruments, including LiDAR. And eventually, what you get is a 3D reconstruction of your plots together with some other measurements, like RGB images, hyperspectral, thermal, etc. And basically, what we do is we change the way that we process the data. So instead of working with pixels like we normally do with your images, we are going to be working with voxels. This is pretty much like pixels in 3 dimensions. These are boxes that define where the canopy is distributed in space, and we can count how many points we have in every pixel. In every voxel, the boxes can have different sizes depending on the resolution of your LiDAR. And basically, by measuring the volume of these voxels, we can get an estimate of the volume of your crop. Or we can treat this information in many different ways and then derive different traits. So one of the most interesting traits that we came across, basically because biomass is a key indicator of the performance of the crop. But the problem is that no one wants to measure biomass. Well, first of all, because it's destructive. Every time you go there, you need to cut a part of your plot, of your crop, and then you'll lose that forever. And also because it's very time-consuming, it's laborious, and you don't want to be doing in the middle of the summer, for example. So pretty much we derive different methods for estimating biomass based on this modeling of the voxels, so counting the volume of these voxels per unit area, and then we can derive some regressions between manually measured above ground biomass and the biomass estimated digitally. The advantage, like I said, is that first of all, it's a non-destructive measurement. It means that you can go repeatedly, and then you can measure the accumulation of biomass over time without having to cut your plot. And this has definitely some important implications. But the other is that the time saving that we can get with this device is amazing, because if you have a large trial, for example, like what we had in Australia, you needed 5 persons in one day just to cut the plots and to process some of these biomass cuts, not even counting for drying and weighing and so on, but just to harvest these plots in the field. One person in 2 hours can do the same job by just working with some of these lightweight phenomobiles. I mean, you can think that if you have some autonomous robot or phenomobile, then it can be even easier as well. So it's non-destructive, it's fast, and also it's more reliable, because when you do a biomass cut, the problem is that you only sample a small portion of your plot, while one of these devices, you integrate the full plot and you can get a lot of information as well about the heterogeneity of your plot as well. The other advantage of this LiDAR mounted on phenomobiles or proximal range, proximal sensing with LiDAR is that because of the high resolution, because it's close to the canopy, it penetrates quite well into the canopy, being an active sensor. In this case, we were using a LiDAR that has a red laser. And this means that the chlorophyll, the red laser, is going to interact with the chlorophyll in the plant. So chlorophyll is going to absorb the red light, and therefore we can account for how much chlorophyll you have for each return of your LiDAR point cloud. And the other thing, because we penetrate into the canopy, then we can map also what is the vertical distribution of the light interception, but also of this chlorophyll content. The problem, unfortunately, is that this LiDAR doesn't have a very good radiometric resolution, so it means that we only get a few values of this light intensity. So that means that we are not being able to get like a quantitative estimate of chlorophyll. I mean, it would be possible to modify the LiDAR, but the manufacturer wasn't really interested in this. But yeah, there's hope of using multi-wavelength LiDARs to be able to map different attributes of the biochemistry of the crops, as we do with hyperspectra, only that being an active sensor, we don't have to worry about some of the things we have to worry with the hyperspectral. And then by using this capacity, we can evaluate some attributes of the light interception and the canopy structure and how this changes over time. So these are 2 examples where we can, by repeatedly measuring on an experiment, we can see the evolution of the leaf area density, or in this case, the fraction of the LiDAR points intercepted in the vertical profile over time. But if we take one single point in time, we can see on the bottom picture that every genotype, every variety has a unique profile, has like a unique shape of the way that the light is interacting within the canopy. And again, this opens the door to a lot of different ways to process the data using machine learning or using some more complex radiative transfer modeling as well. So back to Spain, we found that obviously in our institute there's a lot of work on tree crops and perennial crops like olives, almonds, and some Mediterranean crops that are of great relevance over here. And then we found that there were not many solutions that could be applicable to some of these crops. And even if there's not, I mean, the breeding process and the phenotyping process in these perennial crops is totally different to annual crops. We wanted to deliver something that will allow us to characterize, for example, canopy architecture and some other attributes, and that could be used also for characterizing and even making decisions for management. So we built some prototypes for mounting on a tractor, manually operated with the same LiDAR that we were using for wheat. But the problem at that time was also that when you look at available options for running some of these devices or developing these, we came across that there are no open source framework that allow us to capture the data in a standard way. So pretty much, obviously there are people using different solutions for capturing data, but if we want to make something that is repeatable and reproducible, we need to have open source solutions that people can adopt and people can apply. So we start standardizing data formats and so on. So basically, we developed this Open PhenoLidar framework that is available on GitHub using ROS, the robotic operating system, integrating commercial off-the-shelf units for the LiDAR and some low-cost alternatives to expensive GPSs and IMUs. And like I said before, there's a lot now in the market that just a few years ago, to get a decent IMU, you will have to spend 10,000 euros or so. Now you can get a solution for around 1,000 euros. And then obviously the question is how well this compares, and will it be enough for capturing the data? But basically, with Open PhenoLidar, anyone can download or use this tool and use this to integrate their own LiDAR. Because it uses ROS, it's relatively easy to integrate other LiDARs, and this is what we're doing now with some of the new LiDARs that we recently acquired. So basically, it has a web-based interface that shows the user some of the basic information on the GPS status, your trace, the speed, things like that that we normally need to have in the tractor when we're driving. But it's a kind of automatic data capturing system, and we acquire the data. The data is stored in some raw format, but also HDF5, which is really easy to read in Python or R. And basically, when we get the data, this is the type of data that we get, the point cloud that we get into these olive trees. So this is an experiment of different architecture for olive tree plantations. In this case, this is a high-intensity hedgerow tree orchard. And this is the point cloud that we get with this low-cost approach and with this open-source software. So now, obviously, the thing is we need to validate this, and we need to deal with this amount of data. And the problem sometimes, and I'm sure this happens to most of you, when you try to validate digital traits with manual measured traits. In this case, we're trying to compare like a centimetric LiDAR with something that we measure with a ruler and you measure by eye. So this is sometimes it's okay, what compares what? But anyway, in this case, we always compare with the traditional measurements, and for the characterizations of these tree orchards, which has this kind of a shape that you see in the picture, we get around 17 centimeters root mean square error, but you can see that it agrees quite well. And when you consider the validation methods, I was quite surprised and quite happy with some of these results. So now we are working on, like I said before, trying to have like a more autonomous phenomobile or instrument. So we recently received our robot, our phenomobile robot, where we have also the possibility of mounting LiDAR, happy spectral, and so on. And now we are working on the configuration and calibration of this. So I hope that maybe for the next conference we can show some of the results. But anyway, the thing is that these ground robots have the limitation that they can only be applied to relatively small trials. It's not something that we can see at the farm scale. I mean, there's obviously a lot of companies now trying to make robots for agriculture, but definitely if we want to cover more area, we need to go up to the air. And I'm sure we're going to see a lot of presentations in the coming days on people using drones for phenotyping as well. So we started using LiDAR as well in 2015 and say, okay, how does the aerial LiDAR compare with the LiDAR on the ground? Because obviously if you can fly and obtain the whole trial in less time, obviously that is really interesting. And now we are using the same approach here. And the good thing, because of these new LiDARs, now the cost of the new commercial drones with LiDAR has come down dramatically compared with the Yamaha, with the Phoenix LiDAR helicopter that you saw before. And I have to say that I'm pretty impressed with the resolution and the accuracy that we are getting with this kind of low-cost airborne LiDAR. And this is an example of a traditional olive tree orchard in the south of Spain, where you can see the power of the LiDAR to extract the ground, to remove the trees, to extract just the attribute. You can see the 3D structure of every single tree, no matter of the slope of the terrain. You can see the wires. So really impressive for, like a commercial LiDAR that is relatively low cost. The question is, okay, how does this apply when we take it to a phenotyping or breeding trial? So this is an example acquired just a few days ago in one of our trials there in Cordoba. You can see this is a 3D, obviously we only see the 2D, but it's a tilted view. So overall, overall you can see that, it represents quite well the 3 dimensions of our trial. But when we look at a point cloud generated from structure from motion, you can see that it's very similar. Actually, the visual quality of the 3D point cloud from the structure from motion generated from Pix4D is actually even better. So the thing is, okay, is it still worth expending 10,000 euros in a LiDAR, or can we still go with our RGB camera? So when we compare a profile from both methods, we can see that actually the problem is that the airborne LiDAR doesn't penetrate much into the canopy, and this is something we saw in Australia as well. So the dark blue line on the top, that is the point cloud, the profile generated with Pix4D, and you can see the shape of your plots perfectly, and the light blue line is the Zenmuse L1 LiDAR. And you can see that the problem is that when we compare this with some of the LiDAR profiles obtained from the ground LiDAR, we don't see the penetration that we normally see with ground-based LiDARs. And this is a big limitation if we want to do a structural estimates. The problem, again, is that we are not sure if this is a problem with the instrument or this is a problem with the post-processing. Again, we have a black box, which is the instrument. We have a black box, which is the processing software. And we have no way to tell where this is coming from. You can see you can see a bit more detail in the LiDAR, in terms you can see the rows and things like that. But if you want to extract height, or you want to extract some 3D estimates, probably you're not going to be too successful, at least when you have high density plots with an airborne LiDAR. But this requires a lot of work, and I'm looking forward to see if someone is presenting some results from airborne LiDARs as well. However, things changes a little bit when we translate this to trees and we try to apply LiDAR or point cloud processing algorithms to tree crops. And this is where, when we try to apply some of these methodologies in tree orchards, we see very interesting feature. The same can apply in other crops. So for example, if we map tree canopy height, for example, in this image, you can see spatial patterns of trees in the field that are not growing the same. So interestingly, when we compare this with any other vegetation index like NDVI, we see exactly the same patterns. Actually, even better, because NDVI saturates, and normally when you have very healthy trees, well developed, you're not going to see much differences if you are only using NDVI. But when we look at the height, it actually it behaves like a vegetation index to map the spatial variability, which is something that, we think is quite interesting in a crop management scenario. And actually, this is images that are generated from structure from motion, not even LiDAR. So LiDAR has some even more advantages as well. The other advantage that we have combining LiDAR with other instruments, including spectral and thermal, is that if the images are co-registered, and this is quite important, this is why you need to have very good RTK, GPS processing, and things like that, then we can use the height as a mask or for segmentation of the image. So this is an image of canopy temperature in a tree orchard for almond trees. And you can see that obviously in this case it's relatively easy to filter out the ground because it's warmer. But when you have weeds or if the soil is wet, it's very hard in the thermal to separate between the trees and the background. But if we apply a mask based just on height, anything that is about 1 meter is going to be a tree, anything below 1 meter is going to be whatever, so ground, weeds, or whatever. So it makes really easy to separate and then highlights the differences in the trees and the differences in our crop. But also we can use the height map to segment and to delineate every single tree, for example, as we can do here, and then extract the attributes and the distribution of temperatures or spectral vegetation indexes for every individual tree, like in this case. So combining these different data sets is also very interesting. So what we learned over the last couple of years that we have been working with Lidar is that, well, first of all, Lidar and photogrammetry, in some cases, can give you very similar results. The problem is that we need to change the way we process the data. We need to change, start using point clouds rather than rasters for some of the algorithms. And this is something that I'm sure we see more and more. Because of the significant reduction in the cost of the LiDARs and the new technologies, because of robotics and so on, we are going to see more and more new instruments out in the market that can be translated to agricultural applications. And I'm sure that some of you may be already working with some of these technologies as well. When we compare LiDAR and ground, there are huge differences in terms of the penetration and the resolution, and this is very important as well to consider depending on our application. The accuracy of our GPS and IMUs is critical because otherwise you won't be able to overlap the different data sets. But again, the good news is that things are getting cheaper. And in terms of data processing, the problem is that most of the available solutions are black boxes. So we need to go to open source solutions. And this is why I encourage you to adopt this philosophy like we did with OpenPhenoLiDAR. And if you have the opportunity to make it open source and share it with others, I think eventually we as a community can have reproducible data processing and acquisition pipelines. And like with any other remote sensing data, there's a lot of issues with data volume and data processing. But for me, some of the most interesting things is how we're going to be able to use LiDAR as a way to derive inputs for complex traits and complex attributes and input for crop simulation models or radiative transfer modeling. So for example, this is an image derived from the LiDAR of projected plant area index in the tree orchard that you saw before. So this is using LiDAR. The information that provides us the LiDAR is not just the distance and the elevation, it's also the angle and the probability of this laser to be intercepted by the canopy, especially if we have multi-return LiDARs. So by using radiative transfer modeling and model inversion, we can derive how the light is intercepted, and for each voxel, what is the leaf area that we have in that voxel. Or even if we have enough information, we can derive some attributes about the leaf angle distribution. So by obtaining this, we can use this into models, for example, for radiative transfer modeling of remote sensing products, energy balance, and things like that, like you can see in this image generated by ray tracing with synthetic trees using a Helios model, for example. And finally, I think there's a great opportunity for translating a lot of these phenomic approaches into agronomy. If we come from the initial assumption that the phenotype is the expression of the interactions between the genotype, the environment, and the management, and then moreover, we know that there's a time component on that. Phenotypes are dynamic, they change in terms of seconds, hours, or days. Then we can look at this in a different way. Okay, can we derive management by measuring the phenotype and understanding the interactions between the genotype and the environment? And now that we are gathering more and more data for different breeding trials, or in our case, we have access to plantations where we have different combinations of varieties, or even varieties and rootstocks in the case of almond trees, This is what you see there. Every color there represents a unique variety. And within each plot, we have a huge variability in irrigation and water stress. So when we look at for example, in the graph below, you can see the separation of the temperature for 2 different varieties and different irrigation regimes. So there we have our environment or management by genotype interaction. The thing is, now with these technologies, we can apply, this could be like the next level up for precision agriculture. It's incorporating the genotyping information, the phenomics approaches into precision agriculture. And I think this is something that we, as well as phenotypers, we should be pushing forward as well. So that's all for me. I would like to thank again, and thanks my colleagues as well at the Institute for helping with this work. Thank you.
Thank you very much, José. So we have time for 1 or 2 questions. François?
Thanks a lot, Bernie. It's very clear the interest of LiDAR compared with 3D imaging for trees. I think you made that perfectly clear. But in your experience, are there many traits you can get for annual crops? Are there many traits you can get with the LiDAR that you could not get with the 3D imaging?
Yes, I think all the traits related to canopy architecture, you require the information from the LiDAR, but you require penetration and you require light interaction. The advantage of the LiDAR, like I mentioned, is that because it's an active sensor, it's like when back in the old times people used to measure gap fraction with a needle. So it's the same approach. You have a needle, which is the laser that penetrates into the canopy, and depending on the type of the canopy, you can count how many times the laser is touching the canopy. The problem is that these lasers, the full waveform lasers, they are more expensive and less accessible, for example, than the one I was showing. But by having this information and knowing the angle, or like what Fred and colleagues are doing here, by having multiple LiDARs with different angles, you can derive a lot more information that you cannot derive from a structure from motion. So when we use 3D photography, we get a nice 3D representation of the canopy, but we miss out all this information about the angular distribution of the light interception that we get with the LiDAR. So for more complex traits, you definitely need a LiDAR system, for example.
Thank you. Another question? Yes. Oh, no.
Thanks a lot, Bernie. On the LiDAR from the drone compared to the ground-based vehicles, you indicated it's still a black box, the difference in penetration depth. Do you have in mind any systematic studies that you increase the height of the LiDAR from the ground-based system? Or because it surprised me that that's still for you a black box. Yes. Actually, that is penetration differs so much between the ground-based and your drone-based LiDAR.
Yes, so in that case, I was quite surprised. And actually, when we look at some of the information, the problem is that with the DJI LiDAR, we don't have access to the raw data. I mean, we have the raw data, but we don't have a way to process or extract it, at least yet. So the problem is when you look at the data, once it's been processed by the black box DJI Terra, you get the point cloud, but you find that the point density in the plots is much lower than the point density in the bare soil. So somehow, I think the program is doing something when trying to feed the point clouds, is throwing away many points, probably doing some filtering and thinking that this is noise when it's actually not noise. So this is the problem, and we're trying to figure that out. In the OpenFerno LiDAR and other projects, we are now using the same LiDARs just from the manufacturer, the same light box LiDAR that is mounted in that unit, and there we have the raw point cloud. And we are hoping that by getting this data, we will be able to understand much better the capacity of the LiDAR and whether this LiDAR is, if we can get more out of that. But at the moment, we don't really know whether it's a technical problem. Regarding the height, normally if you fly higher, you're going to get less penetration. We have been trying to fly lower and we don't get much as well. In tree crops, because it's less dense and then you can fly on a tilted angle and things like that, then you can get a lot more information from different angles as well, and then get some more penetration into the trees, but not so much in annual crops.
Thank you very much, José. So I think we'll go to the next presentation. So Malcolm Hawksford will present the automated phenotyping of wheat growth and development in the field. So Malcolm, it's your turn.
Okay, good morning, everyone. It's really great to be here, so thank you for the invitation. It's the first meeting I've attended since COVID hit, and it's a really pleasant experience. So I'd like to present this morning the solutions that we're adopting at the moment in my team at Rothamsted for phenotyping of wheat in the field. And we've adopted 2 or 3 solutions, not necessarily unique, but I'd like to explain where we are. So my key requirements, like everyone, is to have a flexible field-based system with high resolution, both temporal and spatial, and you'll see some examples of these as I go through. And critically high throughput, since typically, as we're part of a pre-breeding program, we're looking at many thousands of germplasm types in any one season, and we really need that high throughput data collection. The 2 solutions that I'm going to talk about, only briefly, are the Scanalyzer system, which you can see in the upper image there, and also some of the drone platforms we're using. And we use these in parallel, and we use them in parallel to extract quite similar sets of data, but at different scales, as you'll see. So particularly growth rates, determined by various means, aspects of 3D structure, particularly important when you're looking at a crop such as wheat and you're wanting to develop and extract trait information, is to be able to identify specific growth stages. And then I've also got an example that I'd like to show where we've been extracting canopy temperature data. Okay, so first of all, I'll just say a few things about the gantry system. Some of you will probably have heard me talk about this before. It's a Lemnitech-based system, which has been in operation at Rothamsted since 2016. So it's quite a mature system. Someone said to me last night, okay, is it going rusty? And the truth is, yes, there's a little bit of rust in places, but it's still working, since 2016. Critically, it's a fully automated system and fully programmable. You can program it for weeks ahead and then just walk away and leave it, in theory. Of course, anybody who's ever worked in the field knows that that's not the case because you have to take into account weather conditions, etc. But it is fully automated. It definitely fits the aspects of high throughput. It definitely gives us high spatial and, if we want, high temporal data capture. It has a platform in the middle, which I'll show you in a moment, which holds all the sensors, which has accurate positioning. We have a range of sensors. Critically for us, it's what I call non-invasive. So although it's a big concrete structure in the middle of a field, which is fairly invasive, once it's actually operating, we don't need to go into the field at all. And under some weather conditions, it's quite important to avoid damage to soil structure. There are several similar situations, installations around the world. This was the first one. It's not without its faults, but actually it's proved quite useful to us. So this is the box that's in the middle. You can see that the area that it covers is about 0.1 hectares. We're usually splitting that up because we're rotating crops. But the key point is that we have the sensor platform on this gantry that can move around the field. This is the sensor platform, and we've got a whole bunch of different sensors on there, principally visible RGB cameras, which have been proved to be immensely useful for a lot of what we do. We have 3 cameras pointing in different directions, so not just straight down, but also at an angle. And we use this particularly for a lot of the feature recognition to pick out growth stages. We've got some laser scanners, you'd be pleased to hear. So these are not LiDAR, but they're 2 paired laser scanners. So they each produce point clouds, which we then superimpose, and from that we can get a lot of 3D information. Most simply height, but also a lot more about organ morphology. We've got 2 hyperspectral images in there, covering different wavelength ranges. I'm not going to talk so much about those today. And then we've got a fluorescence imager, which is the large sensor in the middle, which is surrounded by a number of LEDs for producing saturating light conditions. And then we've also got a thermal infrared camera, and I will show some data from that in a moment or two. So a range of different sensors. I say a 500 kilogram payload. We don't fully utilize the 500 kilograms, but nevertheless there is the potential to put quite a large number of large sensors in if we wish. The 3D imagery that we can get from the laser scanners, you can see here. This is just a snapshot taken, not showing the full resolution, but on the right-hand side you can see a single ear that you can extract. So this is in the field. And so we can get 3-dimensional information about, for example, the ear and ear development, as well as I said, measuring height. The initial reason for having the laser scanner was, in fact, specifically to get height information. And what you can see here is a cartoon showing some actual data taken through the season as the crop's growing. And the resolution is really high, within a few millimeters, if we want to zoom in on specific growth stages. However, taking the data that we can extract from such scans, we can look at growth curves and growth characteristics. This was an early example that we produced, looking at a number of different varieties and look at interactions with nitrogen applications, different rates of nitrogen at specific points shown by the vertical lines. And you can start to dissect in great detail the growth characteristics because we've got this high temporal resolution. Okay. Another example shown in this slide is where we used a mapping population to dissect growth stage specific QTL. So again, this totally relies upon high temporal resolution of a large number of germplasm lines. And from this, we successfully extracted several key growth stage specific QTL, many of which hadn't been identified before for wheat. And we published that a couple of years ago. Okay, so I said about the RGB cameras, and in my opinion, been one of the most useful tools that we have on the platform. And in the top part of the panel here, you can see the raw images that you collect out in the field. This kind of illustrates some of the difficulties that one encounters of different illumination, shadows from the gantry, undoubtedly, and a lot of problems with background. So, of course, what you need to do is to start to extract features, and a simple first step is to extract the canopy from the background soil and background weeds, and also to take account of the different illumination conditions. And again, we've published some quite nice methods for doing that. And this is a first step in order to start evaluating the canopy structure and canopy development. And also, this can also be used, as you'll see in a moment, for masking, for looking at other sensors. Here are some examples of some of the features that we have created algorithms for identifying. The one in the top left just shows one of the issues you've got with drones about identifying the different plots. I won't talk about that, but the other images all show different key growth stages. In the middle there, you've got anther extrusion during flowering. On the top right, and I'll show another slide in a moment, you've got ear detection and ear counting. We're also interested, if you're interested in wheat development, you want to know when the ears first emerge, which is shown in the images in the bottom right, for example. So these are all critical growth stages that breeders do need to know about, and if you've got many thousands of lines, it's really good to have automated systems to do this. And this all comes from RGB imagery. Okay, so this is actually showing our algorithm for counting ears. We developed this to analyze data coming from the Scanalyzer, but then we realized we could use exactly the same algorithm to have automated ear counting for any images, and that includes images that we are now deriving from some of our drone platforms. In this particular case, this is an image from a mobile phone, and the sheet of white paper is just used there as a scaling tool. Okay, and this is showing real time, the time to count the ears. So that's a particularly successful application. I want to briefly switch to some of the drone data collection. We've been running drones in parallel for approximately the same length of time, so since about 2016. This is a development of one of our earliest drones, semi-low cost, one might say, where we use RGB cameras, a thermal camera, and we have used multispectral cameras, but I must say that we don't generally use the output from the multispectral cameras a lot. So nowadays, we run 2 RGB cameras, one of which has been modified to be more sensitive to the near infrared, and then we can collect data from those 2 parallel cameras to compute vegetation indices. And critically, the RGB cameras are used for photogrammetry and 3D imaging. On the right-hand side there is an example of the thermal camera, and I'll show a little bit more detail of that in a moment or two. First of all, I'd just like to say that with the photogrammetry structure through motion, we can get very good, accurate measurements of growth rates. Again, we do weekly measurements generally, and in the bottom left there's a calibration with data collected on the ground. So this is now routine for all of our trials, and it's very feasible to collect data from many thousands of plots in a particularly large-scale experiment. This particular one had 25 different varieties and different nitrogen inputs again. And that has also been published. So I said I'd mention a little bit more about the thermal stuff, so this is unpublished work. And we started looking at a mapping population that we knew had resistance to drought. And we wanted to look at water use in the mapping population and across the germplasm. And in this particular trial, you can see on the 2 sides of the image, there's a non-irrigated and an irrigated side. So quite clear differences there in the canopy, the apparent canopy thermal temperatures. And also a lot of variation between the germplasm. And we can actually look at this through the day and see some dynamic characteristics. So one of the advantages of collecting this sort of data from the drone is that you can collect over a wide area very quickly, which is very important because canopy temperatures can change very quickly due to environmental factors. We did become apparent that there was a bit of an issue with the way we were doing this in that in some cases where you haven't got full canopy cover, you have a big interference with the ground temperatures when you're trying to measure the thermal temperatures. I'll come back to that in a second. This slide here shows how those temperatures change through the day. So these are eight different time points through the day. You can see how generally the canopy is warming up as the day goes on. And then in the afternoon, when it became cloudy on this particular day, it decreased. But as I said, throughout all of this data, we do feel there is this issue of an incomplete ground cover, particularly for some germplasm lines. So with that in mind, we've now started growing, we've been growing the same germplasm collection under our Scanalyzer. And in this case, we've used some different masking technologies. As you can see here, there are two different examples of the way we've approached this. One using RGB images to create our mask, and then co-aligning the RGB and the thermal images. This is actually quite tricky to do. It's possible, but it's quite tricky to do. And actually, more recently, we've switched to using thermal images collected during the night time when there's the best resolution between the ground and the canopy, and using that as a mask. So using these different kinds of masks, you can then start to look at the true leaf temperatures, the two thermal temperatures. And this shows some data here over a 24-hour period, actually over several 24-hour cycles, and you can see clear changes in the temperature of the canopy, as would be expected. And although I'm not showing it here, we've got clear genetic differences, genetic responses, and day-to-day variation, and subtle day-to-day variation specifically relating to environmental conditions, temperature, light, vapor deficits, etc. And so it's pretty critical to collect all of that data. But collecting that data over several diurnal cycles gives us a huge power then to start dissecting the responses of water use in the population. So right, just to finish off, recently we've started to upgrade some of that drone technology, and we're now using hyperspectral sensors on a drone, combined with some airborne Lidar, as we heard just previously. And this proves to be quite complex to work with, but actually offers potentially massive high throughput and a massive improvement in the kind of data that we can collect. And this shows some of our processing from the raw data through to corrected images. And in the bottom right, we've got just the straight Lidar point cloud, which we haven't actually used yet for straight determinations of growth rates. So it was interesting to see the previous speaker talk about that. But this shows the kind of quality of the data that we can get. So this compares hyperspectral data collected on the ground with a Tech 5, comparing with two different sensor technologies for extracting NDVI vegetation measurements. On the left, using the system that I mentioned to begin with, so using two consumer cameras to be able to ratio the visible and near infrared, and on the right using the hyperspectral data. And you can see the data extracted from the hyperspectral sensors on the drone, so they're head wall hyperspectral cameras. And you can see we get a very good calibrations, so I'm very optimistic about using that technology. Okay, so just to finish off and to briefly summarize, there are lots of different platforms available, and we can get large scale and highly detailed data. Most critical, and I don't need to tell this audience, is the sensor configuration and the subsequent analysis of that data. But we can get the spatial and temporal resolution now from a lot of different platforms. And you just need to choose the right platform for your particular application. And I do believe that hyperspectroscopy will give us a lot more insights than we currently have for detecting different stresses. And finally, just to thank my team at Rothamsted and a lot of different collaborators, not all of whom are listed here, for all of their inputs into the work. And thank you for listening.
Thank you very much, Malcolm. So are there any questions in the audience? No question. Yes? Uno?
Maybe a very pragmatic question, Malcolm. With your large experiments, how do you maintain the crop rotation under this indeed nice lamnitic system that is not invasive? I fully agree with you, no invasion in the field, but growing so many large experiments, how do you maintain this influence of the experiments over time?
So you mean under the scanalizer? So under the scanalizer, we just separate it into two areas. So we have a wheat crop in one or the other areas every 2 years. I mean, on the larger scale experiments with the which we've been.
No, scanalizer,
yeah.
Because there you are restricted in your area.
Yeah.
So and only 2 fields means you can revisit weed only every 3 or 4 years?
We started off every 3 years, but then I felt that we were just not using enough of the capacity. So we have no problem with 2 years.
Okay.
Regarding using thermal cameras on drones, do you have any other sense of instability of the thermal sensor besides the differences in canopy density and ground cover?
The most critical tip I give is that you need to switch the camera on and warm it up. It's a simple little tip, but I mean that's what we've done. We have monitored the thermal stability in the lab. And providing we do that, it's perfectly adequate.
Okay.
Yes, following up on the thermal, how long does it take in the gain tree for the thermal data to collect? Because I'm always with a ground-based thermal measurements, you have the problem of environment changing and so on.
So it depends on how many images you want to collect, obviously, but in a typical experiment, we can do that within an hour. And possibly less, 45 minutes. I mean, it was sufficient that we could collect over a 24-hour cycle images every hour or two. I mean, we usually collect them every 2 hours, but you could collect them every hour. But there is a delay, obviously. So that can be a potential issue.
Okay, thank you. Yeah, last small one.
Completely different on the traits. You showed indeed interesting patterns of growth and height over time. And in the early data of many years ago, you showed that there's a drop in 2 varieties, Crusoe and Soissons. They at the end of the season, they drop, which, look at the next talk, it was the wheat heads, they say it's dropping, but then it increased again in the height. What is that? And only a few varieties showed it, and later on you had this, at the end of the season, a clear interaction with nitrogen about this dip at the end of the season in your height. Have you any idea what trait is that? What's going on with the plant structure of these wheat plants? Do they drop their heads and grow again, or?
That's a very close observation you made there. Thank you. And probably you're right. They drop their heads and then they grow again. Or maybe it's secondary tillers growing, particularly at the higher nitrogens. I'd have to look at it myself. So I'm just guessing at the moment.
Okay.
All right, thank you very much.
Thank you very much, Malcolm. So the next speaker is Etienne David. So he will speak about the detection and analysis of wheat ears in the field from different imaging systems.
Okay. Thank you very much, Fred. So today I will speak about the high-power wheat eye detection, and it will be more like a brief history of what we did at CAPTE on wheat eye detection. It was my work, and I'm maybe a CAP baby. I started as a research engineer at INRA. I did my PhD with Arvalis, and now I'm working at IFEN. So why wheat eye detection is important? It's because the wheat eye density is an important yield component, and it's a tedious measurement to do in field. It's long, it's prone to error, and there is a high cost when you include everything. So that's why we started to work at CAPTE on this topic for 5 years now, with a first paper published in 2018 with Simon Madec, and we have continuously improved our method since. So what Madec's work showed is that with a classic deep learning algorithm to detect wheat head, we are able to localize on an ideal RGB image wheat heads with a box. If you combine it with an estimation of the distance between your camera and your canopy, you are then able to obtain a wheat head density. So this deep learning network, which is an important part of this process, is an algorithm, a machine learning algorithm, which is trained on a training database. So how does it work? You have a raw input that will come into the network. The network will output a prediction, and then you will have a function to measure the distance between the prediction of the network and the ground truth. And the higher is the loss, and So the higher is the loss, and the more we will update the network weight. So what is important to memorize here is that this kind of algorithms really need to be trained on data. And it is important because our question now is not, does it work? It is working, deep learning to count weighted, but is it robust? And by robust, I mean, does my estimation, my weighted count, is it unbiased to change within an image given as the same protocol of acquisition? In deep learning, it is equivalent, it is named the domain shift invariance. Is it invariance to shift in domain? So it means that what we want is not, we don't want our deep learning model to be as accurate as possible. We want it to have a random error, so it doesn't depend on the cultivar we want to measure. And it's important because when we go to weighted to phenotyping data, our data is very structured depending on the session of acquisitions. A session of acquisitions is a set of images acquired over with the same vector on the same time unit on the same experimental unit. And within this fixed unit of diversity, the acquisition conditions are controlled, so it's the same vector, same sensor, same illumination, same resolution, more or less. And the factor of variation of the scene are more or less controlled depending on the trial. So it means that the content of the image will vary with this degree of freedom. And if you don't take it in account, it means that maybe it's the reason why your deep learning algorithm can be biased. So we had an intuitive perception of it when trying to scale the work we did with Simon Madec. And in some session of acquisitions, it wasn't working because of the ounce of the weighted, because of the change in the sensors, in the vector. And the reason why is that the training or the diversity of our training data sets was too small in comparison to where we wanted to apply our algorithm. Yes. So to overcome this issue, we work a lot at CAPTE to collaboratively create big weighted data sets. I'm happy because in this room I have many of the people I work with to create these data sets. So we gather data not only from Arvalis and INRA, but also data from Queensland, Tokyo, Saskatchewan. We had some data from Rothamsted, we had some data from ETH, from NMBU. And it means that we scaled for Simon's paper, we had only 3 sessions of acquisitions, so 3 different dates with one vector. We scaled to 47 sessions of acquisitions from 16 different institutions, which represents also a lot of images, so 6,500, and a lot of diversity in terms of weighted. So now we really can account for all the diversity for weighted counting. And I was then able to try to measure this data shift because we had an intuitive perception of this domain shift, and we wanted to measure it. To do it, we did a small experiment where we split our 47 sessions of acquisitions in 2 data distribution. So one source distribution, it was 18 sessions of acquisition from Europe, and the rest was in the target distribution, so weighted from Asia, Africa, and America. Then we trained 2 models. One model is called the in-domain model. It's trained jointly on data from Europe, from the source and target distribution, so from Europe, Asia, Africa, and America. It is called the in-domain model because it will be used as a reference. Then we train a second model, the out-of-domain model, which is trained only on Europe. And what we want to measure is the difference of performance between these 2 models. Why? Because the out-of-domain model, trained only on Europe, should be biased towards the genotype in Europe, the vector we use in Europe, the sensor we use in Europe. Both of them are evaluated only on data from the target distribution, so from Asia, America, and Africa. Just to model it, I did a map. And we split the target distribution in test into two sets. One test set which is used for the final evaluation, and one which is used to calibrate the hyperparameter of the algorithm. So for this experiment, we used a classic yet robust detector, which is faster RCNN, and our criteria to say if a predicted box match a ground truth box in the intersection of a union. It just means that if a predicted box overlaps a ground truth box above a certain threshold, it is considered as a true positive. So for each session of acquisition in the test dataset, we can calculate an accuracy, which is the average of the accuracy per image, which is the ratio of true positive and true positive plus false positive plus false negative. So shortly, the results really show that even if the out-of-domain model performs quite well on some sessions, the more difficult is a session, so the difficulty is the performance of the in-domain model, the higher is the bias with the out-of-domain model. So it's a more rigorous way to show what we already knew intuitively. That's if we don't care about the diversity of the training datasets, our model can be biased, so it can fail in new situations. Okay, so that was interesting for scientists, but now we want to make it work. We want to make it robust, to scale it. And to do it, we call for help to external data scientists, and we created two data challenges, one in 2020 and one in 2021. Both of them gathered a lot of competitors. And the goal here is really to give the key of the problem to an external community which is maybe more used to data science, to see how they can find some tricks, some crazy idea to solve the problem of weighted detection. The result was a little bit surprising in the sense that no crazy research idea outperforms the other, but the winning solution really consists of a lot of clever engineering tricks. And one of the most interesting and the most common tricks was not to have only one model, but to train several models and to merge all the solutions. And how you train several models? The best solutions, they train several models on subsample of the training session of acquisitions. Model 1 is trained on session 1 and 2, model 2 is trained on session 2 and 3, etc. So with this challenge, if we compare to our faster RCNN, which was trained accordingly to what we did in Madex's work, we continuously improved our accuracy. And what is interesting is that the last solution have a very good balance between the false positive rate and the false negative rate. But overall, the accuracy is not close to, was not perfect. We assume it was also because some of our test data was very difficult. So we tried to expand our evaluation on field data. And we gathered a dataset in collaboration with the University of Queensland, consists of 5 dates of frame. So in each frame, we have an in-field human count, we have an in-image count by a human, so the label, and we also run the winning solutions of the challenge, so we have the predicted count. It means that we have 3 sets of measurements. We had 3 sets of measurements for the same frame, and we tried to evaluate which one was the best. And actually, it was difficult to find what was really the reference here, because if you compare 2 by 2 all the different sets, we had an error of approximately 20%. Luckily, we have some statistical method. So this one is called the extended triple collocation analysis, which can allow you, when you have 3 noisy sets of measurements, to access to the error from one noisy measurement to a true value. Normally, it's valid only if your noisy measurement is a linear correlation to the true targets plus a random error. And in our case, it's sure that the in-image counting, human counting, and the predicted counting, because it's predicted from the same images, are more or less correlated. But from what it shows us, that actually the predicted counting from our model was maybe more valid than the labeled, because sometimes it is very difficult to label the weighted with all the ons. So the evaluation of these models are still an open question if you want to be 100% confident, but it already shows that we approach the accuracy of human. We also scaled the global weighted dataset to UAV. So this is a work from Kavya Velumaniz, which was a PhD student at IFEN and INRAE. And she trained this kind of deep learning algorithm on the global weight, but to be applied on UAV platform. So the main difference is that with UAV, we have much less RGB resolution. So we had to find ways to cope with this issue. One way was to maybe evaluate another family of algorithms. So moving from object detection to count to direct regression from the images. So from the image, you predict a density map. From the density map, you predict a number of weighted. And you also have to prepare your data sets to be closer to the real resolution of the UAV. And in place of using a simple bicubic downsampling, we used downsampling combined with a Gaussian blur to really account for the kind of noise you can find in UAV. So the result is that compared to, if we compare to in-image annotation from UAV, we have very good results, both with faster RCNN and the regression method SFC2net. SFC2net is slightly better, so approximately 15% against approximately 18%, and maybe less biased. When we compare to the human, to the in-situ manual density, to the manual counting, the truth is much more blurry because we have our correlation coefficient is quite low. It means that at this stage we were not very sure on our method or on the human counting. But overall, the broad sense heritability was a little bit higher for the deep learning method. So now thanks to the advance in UAV at IFEN, we more work on expanding the object detection approach because we have much more resolution. It's not, so the performances are also improving. And it's also a question of being able to audit the results. When you can really localize the object, you can also really find why the algorithm is succeeding or failing. And I think it's the interpretability of the model is as important as the accuracy. So to conclude, should you stop weighted counting manually? Probably yes, if you have a phenomobile, because the image quality is really good, the lightning control, and the lightning control combined with the result of the global weight challenge made that it's really easy to have a very accurate estimation of weighted. It's probably true with literal too, but you don't control the lightning, so maybe you have to be, so literal is a device that will be presented after. You just have maybe to be more careful about when you acquire your data. And I think today it's true with some UAV. So there is a huge question on the image quality. Some UAV cannot provide you the quality, the necessary quality, but some UAV with the right procedures can provide you enough quality to count weighted. So there is really an needed work to ensure the optimal resolution, to find the optimal camera parameters. Both for literal and UAV, it's better if you can fly or acquire during an overcast day. And the stage, the phonological stage, is super important if you want an accurate precision. Thanks.
Thank you very much, Etienne. So we have time for 2 short questions. Yes. Sure.
Thank you, Etienne. Very interesting. So the UAV data that you presented was simulated only, or was it also actual UAV flights?
No, it was an actual flight.
Ah, okay.
Yes, just that we had 2 sets of validation. The one set was labels we did on images, and there is a label we did on images, and the label and the in situ manual counting.
Ah, okay. Yeah, excellent.
And we had a bias between from moving from the in-image counting to the in-field counting.
Yeah, we've also seen differences in in-field counting, especially in high productivity areas, potentially related to secondary tillers or something. I'm glad you added that last one. I was going to say we tried weed counting from UAVs in sunlight, and it was completely impossible. We thought maybe it was the wind, but I think the light angle and the reflection makes it...
I think the reflection of light on the tip of leaf really look like wheathead at low resolution.
Yeah, maybe.
There is a question in the back.
Okay, if there is one question, that's good because we will win some time. So anyway, we are...
Attends, il y a une question.
There is another one. Où ça? Ah, sorry. Okay, good.
Yes, a very nice Etienne. One problem that we never really solved with the ear counting from the drone is how you scale for it on an aerial basis accurately enough.
So, can you repeat? I can't...
Comment tu mets à l'échelle pour avoir la résolution en fait?
Is this one better? Oh yeah, this one works. Yeah, the issue is from the drone that we've never really satisfactorily resolved is how to scale an area. So if you're flying the drone and you're flying it over a lot of plots and you want to do the ear count measurements, okay, so if you've got good resolution, which is the first problem, okay, I agree, you can detect the ears, but then you need to quantify that in terms of an area. And I never really solved the best way of doing that.
L'estimation de la surface?
Ouais, la résolution, quoi, la surface.
Yeah. So we did some. Actually, we tried to sample the whole microplot, and then sometimes we extract. So from this estimation, it gives us the resolution, and then sometimes we extract a more central part of the plot to avoid the border effect. Yeah, but we can talk also about it during the coffee break.
So I think now we can start the session, the second phase of the session. So the presentation is by Gaëtan David, who is working at Arvalis, and he will present a new system, handheld system, to be used for phenotyping plants in, let's say, small to medium-size experiments. So, you can start.
Okay. Hello, everybody. Nice to meet you. My name is Gaëtan David. I work in the Seagull team from Arvalis with Benoit de Zedde, Samuel Thomas, and other people. I'm here to present you the literal system, which is a light phenotyping system developed since 2019 in Avignon in collaboration with INRA, Arvalis, IFEN, and other partner institutes like GVS, CTFL, Terrinovia, and ITB. So what is literal? The objective of literal is to propose a phenotyping system less expensive than Phenomobile, less heavy than Phenomobile. So it's easier to develop the system in a lot of different places and trials. And comparing to the drone, the objective is to have a system who is really easier to use. And you know, maybe to drive a drone, you have to train. And the objective of Literal is one day training to be ready to use the system. So the plan of the presentation today, it will be in 4 or 5 parts. First, I will present you what is the system with the different sensors. After, we will see the raw data and how this data is automatically classified. And after, I will present you the processing data chain and the different agronomic traits we can provide. So first, what is Literal? Literal is composed of 4 big parts. First, the carrying system, who is composed of a pole to take the sensor head, and a belt and harness to carrying the pole and the sensor head. This carrying system can be adapted to be used on tree, to detect disease, to be fixed on a tractor. And in this configuration, it's to be used on classic microplots, on wheat or maize or flax. The second part is the sensor head. The sensor head is composed of 2 RX0 cameras from Sony. These cameras are 15 million pixels, so the ground resolution is approximate at 2 meter high, 0.05 millimeter. The 2 cameras are mounted to be used like a stereo vision system. So the stereo vision permits to produce height map. We will see in details just after. With this sensor head, you have a third camera fixed on the pole at 45 degrees to segment image, and with the 2 other cameras be able to invert some model to calculate leaf area index. The third part is the application on a tablet to control and prepare all the acquisition. So this application was developed by our partner RoboPEC, and it permits equally to automatically classify all the data. It's a big advantage of Literal. I will present you just after. All the data are automatically classified and normalized to be easier to process. And so, Literal, a carrying system, 3 camera RGB, a control application, and a processing chain. Today, we develop with Hyphen and INRA automatically processing data chain. I will present you just after. This processing chain is available for non-partner people on Cloverfield, which is developed by Hyphen. So for more detail, all the data you take with the Literal are geolocalized. So you have 3-meter accuracy GPS in the head. So for each picture you take, you can have the GPS position. And in this head, we have an accelerometer to control the tilt and of the measurement. So here you have the few recommendations we give to the user of Literal to have good data, because on Literal you don't have flash to take picture. So we try to choose cloudy day to take acquisition. And if it's not possible, we avoid the hour when the sun is low. You can see here that's a cloudy day. This one is cloudy day 2. This one is a day with a lot of sun. So you can have problem with the shadow. But today, and we will see just after, with the deep learning model for the segmentation, the detection, we can process data with some shadow. After, the only thing is to take picture on a microplot. You have to position the sensor head on the middle of the microplot. For the sensor head at nadir, for the third camera at 45 degrees, and the sensor head and the 45 degrees camera have to see the same place on the microplot. All the pictures you take with the Literal are displayed on the screen, and we recommend to use Literal 1.5 meter higher than the canopy. I tell you just before the big advantage of Literal compared to a classic RGB camera, that you can prepare all your acquisition at the beginning of the year. And with this preparation, all the data will be classified automatically by trial first in your software. For each trial and each day of acquisition, we create a folder with the date and the hour. In each trial folder, you have some folder for the different microplot with a lot of metadata. And for each folder of microplot, you have all your image. So 1, 2, or 3 images for 1, 2, or 3 different cameras. With all this automatically classified data, you have a lot of metadata. So the GPS position, the tilt of the head to control the quality of the data, and the name of your trial, a lot of metadata. So the third part of Literal is the processing data chain. Is composed of some individual modules combined to define a full processing chain. So some of these individual modules will be present today or tomorrow by other people, but a non-exhaustive list is the raw data. I don't tell you. At the end, the raw data are stored in HDF5 format, that is compressed format with the data and some metadata. So the first step of the processing chain is to extract the data. After, we can pre-processing, so enhance the RGB image, and after run some individual module with deep learning detection of spike head, of emergence plants. Segmentic segmentation with vegetation, two-class semantic segmentation with vegetation and background. Three-class segmentation with weeds, crop, and background. multi-species segmentation, or green part of the plant, yellow part, and organ part. After we have raw detection and stereo vision that permit to with the counting module, we can count objects on the image. And with the stereo vision and the raw detection, we can transform this count in density. And after, with the stereo vision module, we can produce point clouds and height map. You can see some example just here. I will present you a practical example. In Arvalis, since 2 years, we stopped to count the flags at emergence manually, and we just count flags with literal. So you can see here some example of image. It's a really big part of the. No, sorry. So to image the processing chain, you can see here an example. So first we have the raw data, the image. After we run the segmentation module. After the stereo vision module. So with these 2 steps, you can have the real resolution of each pixel in the image. After, we can select the area for the counting and the raw detection. Oh, sorry. So with the stereo vision and the segmentation, you have the real resolution for each pixel. With the detection, you have the number of plants on each image. And with these 2 information, you can have the density of plants for each image. So that's what we want. An interesting fact with literal, here you have two plots. The first one is the comparison of the flags counting at emergence with literal and human counting, but exactly at the same place. So we have some repair on the microplot, and human and literal will count the plant at emergence at the same place. So you can see that the availability of the counting is quite good. And the other plot here is not the counting at the same place, but for the human, they count the plant at the same place of this one. But for literal, we make the average of the fourth photo we take on the microplot. And you can see that you have a negative effect because human always shows the place on the microplot where the plant grows the best. Then with literal, you have a real and representative average of the traits that you measure. So that's really interesting to see something like that. And the last step of the literal, so I present you is some module to produce some traits, individual traits. And the last step is to validate statistically all these different results. So we have an automatically statistic validation chain that tests the different repetition of each variety on your trial. And it gives you for each plot if one or one other traits are valid or not. And so here you have the progress of the different agronomic traits of the Seagull team. So you have, with literal, so you have all the traits for the light interception are statically validated and produce for each and in production. For crop architecture, you can read this. We can discuss after. So we have 3 types of development: in progress, in validation, and in production. Today we produce with RoboPEC 50 systems, which may be 30 for Arvalis, because each station of Arvalis have 1 and some stations have 2 literal systems. A lot of development are in progress with hyphen, INRA, and user partner. And today, the literal I will present you more maybe at Greu is, I think, the version 3. So it's a final prototype, but we discuss with an industrial partner to have a real industrial version, maybe for next year. Thank you very much. And if you have some questions.
Thanks very much, Gaëtan. So, 1 short question, maybe 2. Yes?
What about the calibration of the zero vision?
Yeah. Each system is calibrated for the stereo vision, and the calibration matrices are provided for each system. If you sell 1 system, is automatically calibrated.
Oui. Cameron?
Thanks, Gaëtan. I just wanted to know why we used the inclined angle in literal compared to nadir angle, because most of the time we see nadir angle the best angle to taking images.
Sorry, I don't...
Why using another angle?
As a 45 degrees camera, it's to use with the Fred model, Pro Sail, who... No, with the 45 degrees camera, we measure the leaf angle. And with the leaf angle, after you can inverse the model to have the FIPA, LAI, and all the light interception traits.
Okay.
Yeah.
Thank you. So I will not present the next speaker. I will gain some time. Ouais, c'est moi, ouais. Oops. Okay, so I will try to discuss the interest of process models or data-driven, let's say process model-driven or data-driven approaches to estimate some state traits. So in the program, it was not exactly the same title, but it's about the same idea. So it's a common work with the colleagues that are listed here. So just to say that when you try to estimate a trait, so how it works there? No. Ah, yes. So you have a canopy with each structure and properties and the let's say the observation conditions, and this is actually some kind of set of physical transfer processes that drives the observations that are recorded by those different systems, phenotyping or remote sensing. So it's going in one way from the description, let's say the state of the canopy to the what you observe, like reflectances, for example. And so if you want to go the other way, so from the measurements to the variables of interest, you have to inverse those kind of processes that can be simulated by models. And of course, this is an inverse problem, and inverse problem is any kind of inverse problem is generally difficult because it's ill-posed. That means it's there are many solutions, several solutions that may correspond to the same observations. So you have to choose what are the solutions that you will retain. And so you have to constrain the problem. So to solve this problem, so that's what we did in remote sensing, but for phenotyping, for at least many traits, is the same problem. You can use a model here, like a radiative transfer model. If you are interested in the Liffer index, the radiative transfer model simulates the reflectance from the Liffer index and other variables, of course, of the canopy. And then you have to invert this model to retrieve the actual LAI. So this can be done with machine learning, very efficient, like simple linear regression, support vector machine, random forest regression, neural network, GPR, etc. There are many, many techniques. And these techniques are the ones that are minimizing actually the difference between the variable that is retrieved, the estimated variable, and the one that you have in the training data set, that is the variable that is used to simulate here the reflectances that are input in the inverse model. So the inverse model has got coefficients, and what you are doing is to adjust the coefficients so that you minimize the distance here, which is a bit different from another technique that is used for at least a very complex model that are run in different configurations, where it's based on optimization in the space of the observables. So here you are trying to find the minimum distance between the observations, and then you play on the parameters like Liffer index, but other parameters or input variables of the model, to minimize this distance. So it's a big difference, and this can be done with iterative optimization, lookup table. And what we found is that, generally speaking, when we compare those two approaches, the machine learning approaches are more efficient because they perform generally better, especially for the traits that are more complex. And of course, they are faster to compute. Because it's not iterative, even though the lookup table is not iterative, but you can have large tables to handle, which is not very convenient. So what you can also do, of course, rather than using a simulated training data set, simulated with a model, you can use an experimental training data set made of measurements, and you do the same thing, and this is what most of what we are doing is correspond to that, with some problems because you may have some overfitting, because the training data set is not representative of the ensemble of situations. The learning process is not well designed, and the inverse model may be also too complex. Too many coefficients to tune, so you may have some problem this way. Okay, and the problem when you are using experimental training data sets is the problem of the causality, because you can, with those machine learning techniques, you can relate whatever you want, and sometimes you are relating things that are not really causally linked. Which is generally not the case here, because you know what you are doing. You are controlling exactly the processes through the model that you are running. And to understand the causality, you can use the process models. So I will illustrate that with two examples. So first example is when you are using multispectral cameras over crops. When the reproductive organs are appearing, what is the impact of the reproductive organs on the response? on the radiometric response, and of course with consequences on the estimations of the traits that you are interested in. So we made some experiments with UAV. We acquired bidirectional reflectance values, and then we cut the reproductive organs and make the measurements before and after cutting the organs, and then observe the difference here for wheat, maize, and sunflower. So you see that there are differences. So the colors correspond to this is in the red band, 675 nanometers for 3 directions. And you see that there are effects, at least for maize, but there is some noise, so it's difficult to understand if it's coming from the measurement error or if it's something that is actually observed. And for that, we can use simulations, 3D simulations. So we simulated as realistic as we can canopies with those reproductive organs. And then we removed the organs and did the same thing, try to simulate the reflectance. And then we see that the trends are quite similar. Of course, the noise is not as important here. So this allows us to say that maybe for wheat and sunflower, maybe it's not a major problem, but probably for maize, because the optical properties are a bit different, that may be a problem, because the difference is quite significant, both for the measurements and for the simulations. Another example, to try to understand which quantity is best estimated from, let's say, reflectance measurements. We don't know if it's the leaf area index, so just the leaves, or if it's the green area index, so the leaves and the stems or branches and whatever, or if it's what we call the effective green area index, so what we could measure if we assume that the elements are randomly distributed. So this is, for example, what we extract from when we are using hemispherical photographs. We make these assumptions, or we can make these assumptions, and we get, in this case, the effective green area index. So we made pseudo experiments on wheat and I don't know why it's not working. Okay. On wheat and maize, and compare the truths, because it's simulations, it's the truth, it's what we entered as input, to what we estimate by inverting the model over multispectral observations. And we see that if we look at the R square, the effective leaf area index is the one that is best estimated as compared to the leaf area index, where you are missing the stems that account for the radiative transfer, and the GI, because when you are looking just from nadir, it's difficult to get a good idea of the clumping of the leaves. So it's why we get better estimates from the effective leaf area index. Okay. Then we can also use process models to optimize the observational configuration. So for that, we used model simulations. So we constructed with Shu Yang, a student that now is working at University of Nanjing, what we call the digital plant phenotyping platform. So we start by the description of the canopy state, the let's say meteorological information, the sunset configuration, into a plant model, 3D plant model that simulates the structure, the 3D canopy structure. And then we can simulate with a different model the RGB images, the Lidar point cloud, and the multispectral images. And from that, of course, which are similar to what we can observe, and then we can relate the emerging properties like leaf area index or green area index or whatever to these pseudo observations. And what we did here was, that answers partly to the question from Kamran, If we are interested in here green area index or the average leaf angle or the FE-par, the best combinations here it's the matrix of a square of the corresponding to the RMSE, or when combining two cameras, one looking at a specific angle and the other looking at another angle. So these are the angles here, and you can see that the model says that the best configuration should be one camera at 60 degrees, and the other, depending on the trait, could be between 15 and 45 degrees. However, what we even though the model says that, for practical reason, we are choosing this configuration, which is actually not too bad and not too far from the optimal one. Process model can be also used to validate traits that are difficult to measure. So that's what we did with Lidar. So it's part of the what Raul will show in detail. I don't know when, just after, I think. So with the PhenoMobile, we have LiDARs on it. And from the LiDAR, we are able, by also using a more simple gap fraction model, we can evaluate what we call the plant area density, so the area per unit of volume that we have in all these small voxels. So we can validate only the PEI, so the sum of the PAD over the crop, but not the local PAD because it's very difficult to measure. And for that, we use again the D3P here to simulate the point cloud and then cut the small cubes, and then count the area in the small cubes and compare with what we get from this the model inversion that we set up. So these are some results. We see that this is the truth, and this is what we estimate on each of those small voxels. So if we have small voxels, we have good results. If we have bigger voxels, results are not so good, probably because of some clumping. So we have encouraging results, and what is more encouraging is that when we compare to what we can actually measure here, from the simulated, of course we have a good match because we already had a good match at the plant area density level, so at the PAI, of course, we had a good match. But we also have a good match on the measured PEI, measured in the field by destructive methods or hemispherical photographs. So this is a way to validate. So I come to the key question. So is a process model as good as data-driven approaches to estimate some canopy traits? Okay. So I will illustrate by a few examples. So that's why I changed structural trait by state traits, because I was speaking here about biochemical traits, which should be in the second session, but anyway. Okay, so we made, so the question is, with a leaf optical properties model, could we get a good enough estimate of the chlorophyll content and water content at the leaf level? So we made measurements at the leaf level here in the lab. So these are examples of spectra that we measured with the integrative sphere. We have a model, the prospect model, that describes the physical processes in a simple way, but quite effective. So you have the inputs here and the output, which are the leaf reflectance and transmittance. And these are the results here. When we compare for chlorophyll here and water content, the different versions of the prospect model, and here different indices that are extracted from the literature that should be connected to those two traits. We see that the models perform generally as good, or in this case, slightly better than than the vegetation indices that we found in the literature. Okay, this is true for, let's say, the stronger absorbers like chlorophyll and water, but it's not true for the weak absorbers because it's much more difficult to describe the signal. The signal is very weak, and actually the empirical approach, so the data-driven approaches are much more accurate because they are taking into account some covariability between different components that is very difficult to take into account with this process-driven approach. Okay. Second example, when we estimate with remote sensing, but could be also with UAV or multispectral cameras on a phenomobile, when we estimate green area index or other variables, in this case it's green area index, from Landsat or from PlanetScope, so 3 meter and 30 meter resolution, we can use either data-driven approaches. So we measure in the field the green area index, we have the satellite image, and then we relate empirically the two. Or we can use model-driven, so we invert even a simple radiative transfer model to get an estimate of the GI. So in this case, it was done on 900 plots distributed over the world for different crops. Rice, maize, wheat, sunflower, soybean, and other crops. It's a mixture of different crops. Here we test, here we train. So it can be either generic, so we train over all the species and we test on each individual species, or specific, so we train on each species and we test on all the species, but particularly on the species where that was trained here. And we can use also model-driven approaches that is generic by nature. We can make it more specific, but actually it's quite difficult with those simple models. And we get the results, and we see that each time the specific data-driven approach was much better than the generic one, and specifically the generic model-driven approach. The same was the same. No, not exactly the same for wheat with PlanetScope or 328 plants in France and China. The data-driven approach was slightly less accurate than the model-driven approach, but actually in this case they were quite close together. Okay, so generally speaking, the data-driven for this case are generally working slightly better than the model-driven approach. Because of course they are we are using a simple model, we didn't take into account let's say the complexity of the canopy structure and optical properties, which are implicitly taken into account in the data-driven approach. And here specific models are also preferred, of course, for the same reason. Another case, so it's a study with Etienne. With UAV, we try to identify the plants, to count them for wheat, for maize, sugar beet, and sunflower, so big plants. So it's a simple problem because, okay, it's easy to see, but anyway, it's not so. So we for each species we have 9 flights distributed into 3 stages. The images were about 5 millimeter resolution, and we labeled quite a lot of plants. And then we applied a process-driven approach. It's a handcrafted method, which is some kind of process-driven because we know exactly what we are doing, because we know a priori the shape or the size of the plants, the distance between the plants, or we can tune it by the observations. We know that they are in rows and so on. And we know that they should be regularly planted, so it's easy to identify gaps. So this is the basis of the process-driven approach. And we tested also a fully data-driven approach with deep learning, so it's a faster RCNN algorithm that was pre-trained on COCO dataset. And these are the results. Okay, so for maize, sugar beet, and sunflower, you have the handcrafted method, so the data-driven, process-driven approach, and the deep learning approach, which is the data-driven approach. And you see that in most of the cases, again, the data-driven approach is performing better than the process-driven approach, because there are cases that are difficult to handle. And also one strong limitation is that with the segmentation, the quality of the segmentation between the background and the plants is very important for the handcrafted methods. And in some cases, we had problem with segmentation, which make the drop in the performances. So the limits of the process model-driven approach, anyway, it's the realism of the plant model. So the representation of canopy structure and the optical properties of the elements. The rendering of the scene, here it's not too much a problem because now we have very good tools, radiative transfer models or rendering machines that are very efficient. And the one big question is the description of the space of canopy realization. So how to distribute, how the data distributed in terms of representativeness regarding the true distribution of the input variables. So this is really a big problem. There are ways to improve the realism of the simulation. So this is taken from the presentation of Shuyang tomorrow, where you can start with a simple representation, input the light conditions, input the soil background, input the leaf texture to get more better realistic, more realistic images. You can also make some kind of domain adaptation to reduce the domain shift between the simulated images and the actual images. So this is done with cycle GAN, so I don't go into much detail because this will be also presented by Shuyang. And we can see here that without domain adaptation, when you use raw simulated images, we have relatively good performances for, here it's the first stages, 1 leaf, 2 leaves, 3 leaves, 4 leaves, because it's a simple problem here, but when it's a complex problem, the performances are dropping. And when we adapt the domain with the cycle GAN, then we increase a lot the performances of the methods. So that's first conclusion. We need there is a need for process model to understand the causality, and this is very important in many cases, through sensitivity analysis to optimize the observational configuration, even though sometimes with practical details we choose other configuration, but we could put that into as a constraint when we choose the configuration, and to validate the methods that are difficult to validate in the field. So the question was, are process model or data-driven approaches better for trait estimation? So the interest of process model is that you constrain the inverse problem by the knowledge that you input through the models, but it's limited by the realism of the models. Sometimes the models are too simple, but you can adapt the output with adaptation techniques, domain adaptation techniques. The problem of the distribution of the input variables, and specifically the co-distribution between the variables, it is very difficult to get things which are realistic because we don't know them more. And then the ill-posedness, so the fact that we can get several solutions corresponding to one observation. This is, for example, a problem when you are looking from nadir with a multispectral camera or just with to get the transmittance from the canopy to estimate green area index, because there are confusion with the leaf angle inclination, for example, and other traits, but mostly this one. The data-driven extracts the information all, or maybe not all the information, but a large part of the information from the measurements. But there is a problem of the causality, so you can relate things that are not causally related, which might be a problem if the covariance that explain your good relation or good results didn't apply in other conditions. And performances depend on the quantity, on the diversity and the quality of the measurements or the labeling. And this is very important, quality of labeling and measurements. When you train a machine learning or deep learning approach, you may have poor results because of that. And of course, because you want to have big data, you should try to share as possible the data that you get, with anyway some problems of consistency between the acquisition conditions, the labeling, and the measurement protocol that needs to be harmonized. And then I was speaking about the state traits, but of course for dynamic traits, the functional models that are dynamic may be very important to use in order to input this knowledge on the biophysical or ecophysiological principles when you try to characterize some functional traits from your crop. And I think Raul is working on this, and others is working on this very interesting aspect where you mix observations with crop functioning models. Okay, that was the last slide. Thank you.
Okay, I think we have time for a couple of questions. If someone raises their hand. Yes.
Thanks, Fred. Could we imagine approaches with combined process-based and data-driven approaches? Because we know that process-based, you have a lot of inverted commas in process where they are quite empirical, and you put the equation you like to have in, so they are fragile as well. So can we imagine to have something that plays on both?
I think there are two solutions. So one solution was investigated by Raul, is to use a Bayesian approach where you can input some observations in your system. The other is to make ensemble solutions, so you can mix the solutions from your data-driven approach and from your model-driven approach. I think also this is very efficient. So yeah, maybe there are other solutions, I don't know. But
Thank you. Some other burning questions? Okay. I was thinking if I should ask one, but it's okay, in the sake of time. All right, so thank you. Let's welcome the next speaker, Benoit Mercatoris.
Okay, thank you, Mr. Chairman. So my name is Benoit Mercatoris. I'm coming from Belgium. From the University of Liège, but I'm working in a nice external campus of Gembloux, which is a little city in the middle of Wallonia, between Brussels and Namur. And I would like to share with you research activities we have started in 2016 about the monitoring of weed growth dynamics directly in field condition. By using multimodal imaging, and we would like to see if we are able to reach the organ scale by this kind of close range vision technology. So this presentation is the result of different PhD work. So I present here three of my PhD students, Sébastien d'Andry-Foss, Alexis Carlier, Damien Vink, and my colleague Benjamin Dumont, who is also associate professor in crop management and crop modeling. And myself, my expertise is more oriented about mechatronics. Okay, so the content of my presentation will be the following. First, I will speak briefly about motivation and objective of our research, and I will present it our prototype of phenotyping platform, so a kind of little phenomobile which takes inspiration from the phenomobile of Arvalis, and I think also the phenomobile light or Lidar presented by José previously this morning. So I will also, of course, present the multimodal system we use to take different kinds of images, and the traits extraction, and some word about agronomic variables. We are starting to work about that. So we are around Jean Blou. We have a lot of variety trials oriented on wheat, cereals. The idea is to develop a tool to assess this kind of variety trials in order to monitor the growth dynamics of the crop in the fields, and try to have a cost-effective vision and try to work in natural conditions. And so the idea is to monitor all the growing season here to take the different component of the yield development and see the interaction between different stresses, abiotic and biotic stresses. So the objective of this presentation is to try to motivate and evaluate a methodology to characterize the wheat morphology and physiology at the organ scale. So the question is, are we able to develop a close-range multi-sensor vision system to work in field condition from tillering to maturity to monitor the crop growth dynamics? So the platform we have developed from scratch is the following one. So the idea is to have something which is modular, transportable, which can be adapted for the different variety trials because it's managed by other teams. So we develop a motorized platform using 4 wheels for steering and driving. The choice was to work in natural light conditions, so without external and artificial lighting. The platform can be controlled by only one person, by remote control, but we have also developed a vision-based navigation in order to follow the microplots line. And for the acquisition, the idea is to trigger in a synchronous way the different camera I will present in the next slide, and also to geoposition the data in order to establish a time series, of course. So the cameras we use, basically, I will present the treatment for each of them, but we use stereo vision in the same way presented by Gaëtan. So this is a GI camera, but the principle is the same. We use a multispectral camera, so a multispectral array of camera. 6 filters are used, classical filters. And we also integrate a thermal one, but we have not yet extract agronomic knowledge from this camera, but I will speak a little bit about that later. And in order to be able to work in natural conditions and take into account the incident light variation, we use a spectrometer. So the first step was to manage with stereo vision. So as you know, it allows you to get a depth mapping. So you have here the main step of the treatment. So the idea is to get the disparity map, so between the left and the right eyes, like you see a 3D movie with your green and red glasses. So you see two different images, and we try to get the disparity between the same object. So for example, the tip of the leaf here. And from this disparity, you can, by triangulation, get the depth of the image. So we are able to bring, to construct RGB depth images at the organ scale, and we segment this in order to get the depth of the leaves, to get the depth of the ear, and so on. So mainly based on color components combined with HSV space, we're able to extract the leaves, and when you have spikes, you need to add 8 estimation and texture descriptor in order to have a robust segmentation. So if you are interested, you can see the paper related to that. So also based on color images, we have developed the ear segmentation and density estimation based on the deep learning model. So we contribute modestly to the global width head dataset presented by Etienne, and we use it to train by transfer learning and pseudo labels to train our own model using a YOLO model. And one point interesting is if you use the DeepMac model, which is not difficult to train, we can also have the segmentation at the pixels scale of the different ear. So in addition to the bounding box. And so thanks to the 8 math from the stereo vision, we are able to get the footprint and to estimate the ear density. So if you are interested, we have our own dataset here, which is available, which is open to use. Okay, so now we have 3 vision technologies. So with the thermal one. And since we have a close range acquisition of image, we need to deal with the different point of view. So we need to develop method to register the different images and to superimpose this and have the information from the stereo vision for the multispectral one and the thermal imaging for each organ. So and ideally for each pixel. So for that, we have tested different methods of registration. So in order to construct an image with different layers of 3D information, of physiology information, and temperature information. So the methods are presented here. And for example, you have the idea of a calibration-based method. So based on the images we have from the different technology, we use this pattern in order to find the homographic transformation matrix, which is depending on the distance. So the stereo vision is also interesting for that. And one originality is to, for example, take a reference target with different material, and the circle are put in the fridge in order to get a contrast in temperature to do the calibration in the lab and to find the transformation matrix. So this here, the example we can have from the different vision, the different technology. So you see that at the same position you are able to put the organ. Here, for example, you have the hair. You see with the RGB images, here the one channel of the multispectral, and here the thermal vision of the same organ. The next step was to deal with multispectral vision in order to try to, it's not easy of course, but to try to go in the direction of absolute reflectance and not relative one, and to use the spectrometer to take into account the variation of light condition. So for that, in order to avoid to use reference panel in each images, which is not very convenient in the field, we have developed a calibration process. So in the lab, or in the field, we use before the campaign, before each day, we use a target here in order to process to compute the calibration curve, the response curve of each camera, each channel. So the process is here. We measure the incident light with a spectrometer. We get picture from a reference target of known reflectance. We control the exposure time, and we make the correlation for the link between the digital number of each sensor with the exposure map we have at the entrance of the lens. So once we have did this, we are able to directly in the field, when we have a picture of the width canopy, link, compute from the digital number, compute directly the reflectance of the width. So it's the methodology we use to normalize the reflectance measurement. So example of threats we can extract from these different vision system, multimodal vision system. So here I show you a color image and 2D information we can extract after segmentation. So for example, the leaf ratio, the green and plan ratio. On the same image, you have here the 8 descriptors. So it's like a point clouds you have for each organ in the image. Yeah. A kind of average bidirectional reflectance factor can be extracted also at the organ scale. So it's always the same images. So now we can fuse the different information of color, 8 reflectance information, and in a future work, thermal information. So for example, you can also, of course, compute vegetation indices since you have reflectance information. Okay. So what about data collection? So from 3-4 years, we go into the field with our device. So we have developed the acquisition device, the PhenoMobile in parallel during this year. And we try to take picture at different growing stages. We are working in trial fields mainly where my colleague Benjamin Dumont is testing different fertilization management. It's very interesting for us because it allows us to have variability of architecture, so and a variability of nitrogen content. So you see here in the plot, black and green are related to image acquisition. So we have started with only RGB, and after that, from the 3 years, we have added multispectral measurement, and now we will add it also thermal vision. And of course, image, when you develop your acquisition system, image is not enough. We have also to have reference measurement. This is the cross mark in blue and red also. So the cross mark is very important. So it allows us to take from tailoring to maturity different information from the organ scale. So it's very time consuming, as you can imagine. as you know, in fact. So the main traits we take are the following. So we start now to try to merge all this information we have acquired with this system. And the first things is to explore the different kind of feature you can have. So at the organ scale, so we select here 21, but we can take more, many more. But the first point is to see what, to identify which of them are correlated together or not. An example of variables we have extract is the leaf area index, above ground diameter, and so on. So you see an overview of preliminary results we have on 2 years of experiment. Again, we try also to use deep learning in order to predict agronomic variables directly from the image without extracting manually information. So this is the direction we try to follow to exploit the data we acquire in the field. Okay, so as I said, we will integrate also thermal vision, so the acquisition is ready for that. We try in parallel to work with hyperspectral imaging, so we project to put it on a drone in order to monitor, for example, nutrient deficiency in phosphorus, and in order also to develop a multi-scale approach. And we focus also on disease detection. For example, by hyperspectral imaging, we focus on fusarium on ears. And for that, we have developed in the lab a model, a very interesting model, I think, to detect the presence of kernel inside the ear or the absence. So to touch the feeling of the grain. So the experiment in the lab, of course, consists in removing from a mature ear to remove manually the kernel. So we have a specialist to do that without break the ears. And by means of hyperspectral imaging in the infrared region, we are able to build a model to detect the spikelet in which we have removed the grain. So it's very nice. And we try to develop that to detect fusarium in the field, because as you know, fusarium are impacted the feeling of the grain. Okay, so this is the end of my presentation. I would like to thank my team, especially Sébastien Dandifos, who is finishing his PhD, and I presented his work, and he have published a very nice paper. So thank you for your attention.
Thank you, Benoit. We have some time for questions.
Thanks, Benoit. So that was very interesting to see how you can combine all the images together. But actually, which traits benefit from this combination?
Yeah, that's the following question we have to answer, indeed. The idea is to see what is the added value we can bring to that, to the community with this. For my feeling, it's remain low cost, and we try also to be independent from the consumer, the producer of camera. So we combine the different things. Yeah, this is the main spirit.
Thank you. Some other questions?
Hello. Yeah, it's working. In fact, I have a small question because in the images about wheat heads that you have shown in your presentation, I have seen that organ is quite in early stages of development. So should I assume that the programs that you developed, they are more functional, or they are more, they give optimal results when the imagery is taken in early stages of organ development?
Sorry, I have an echo and it's difficult to understand.
So most of the images or most of the examples that you have shown in the presentation, I observed they are taken in early stages of organ development. So should I assume that your programs, they show optimal results when imagery is taken in early stages of organ development?
I'm not sure too well understand. You mean
the stage of organ development, at which point it is important to get optimal results from your programs?
At which stages, you mean?
Yeah.
Okay. Yeah, the idea is to monitor during all the seasons. So it's not to focus on one stage. So at each stages, we would like to extract the main information we can have from the different sensors. So there is no going stage at which we would like to optimize the acquisition. But I've shown it is shown in different papers, but we test for example, the evolution of the ear counting during the season, and we see that it's not constant.
Yeah.
And so sometimes it's depending on the acquisition parameters, sometimes it's depending on other information. But yeah, this not. I have no answer to that. But we can discuss after.
Yeah.
If you want.
Thanks.
Okay, I think it's time to move to the next speaker because we're running quite over the schedule. So let's welcome Raul.
So, good morning, everybody. So my presentation will be about a synthesis, a summary of the activities that we have developed at the CAPTE team in close collaboration with other units from INRAE and from Arvalis in the estimation of architectural traits from LiDAR. So in my presentation, I will start with a brief introduction on how we use LiDAR with PhenoMobile, and then I will briefly describe some methodology and some examples on how we use LiDAR with PhenoMobile to estimate traits like canopy height, canopy transmittance, and the 3D distribution of plant area. So, as Berni explained very well this morning, the LiDAR is essentially an instrument to measure distance, and what we get when we sample our surface is a point cloud, a digital elevation, a very detailed digital elevation model of, in this case, of our canopy. So it's an instrument to measure distance, but we additionally use for other purposes. So the PhenoMobile is the vector that we use for LiDAR acquisitions, where there are different PhenoMobile versions. But basically, what we have is 3 LiDARs mounted. 2 of them are looking at nadir, and 1 is looking at 45 degrees. The footprint of the 3 LiDAR have a substantial overlap between them. And basically, in the PhenoMobile, they operate like a push broom sensor. So there is a scanning direction, which is perpendicular to the rows, and the head moves in the direction parallel to the rows. And the PhenoMobile stores, thanks to a differential GPS, the position of the LiDAR and the distance to the impact, the reflectivity, and so on. Okay, at the right side we have a typical acquisition on a width microplot of the three lidar. As we see, there is a very dense point cloud, and for each beam we know, thanks to the GPS, the coordinate x, y, z of the lidar position, the coordinate of the impact, and also the intensity of the backscattering. So on the three lidars, thanks to a calibration, the impact of the coordinates and the positions are in the same coordinate system. And thanks to this position of the coordinates, we can trace back the trajectory of every beam, and as we will see later, this is essential to compute canopy transmittance from LiDAR. So, as we said before, LiDAR is an instrument to measure distance. So one of the most immediate traits that we can estimate from LiDAR is the canopy height that can be derived directly from the point clouds once we establish, well, more or less empirically, the distance between the sensor to the ground. And as it has been demonstrated in previous papers of some colleagues, the measurement of canopy height by LiDAR is highly repeatable and heritable. So we have very small variations between replicates of the same treatment. This is a nice example of an experiment in the previous year. We have 10 genotypes and the same environment. It's a well-watered environment. And we can see very clearly the difference in the final canopy height of the 10 genotypes. And also, with the dynamics of canopy height, we can track very well the different level of precocity of the varieties, especially during the stem elongation phase. So it's, in general, a measurement that is quite clean and highly repeatable. Apart from this, the final height, what is interesting is that we also can link canopy height to the response to water stress. This is a result from the same experiment. We have two cultivars with more or less the same precocity, and we can see for the difference in the blue line is the height dynamics in a water stress treatment, and we can identify very well how both cultivars response to an episode of water stress. In the case of the second cultivar, the curve, the stem elongation, is very close to the reference well-water treatment in green curve. So it's not only final height, we also can track the effect of abiotic distress in the height dynamics. Well, canopy height is very interesting, but also thanks to the LiDAR, we can compute a physical quantity that is canopy transmittance, which is very linked to the plant functioning, as it gives an entry point to light interception and light absorption. As I've said before, we know the coordinates of the beam origin, and we know the impact, the coordinates of the impact. So if we divide our scene in 3D voxels, we can always trace the trajectory, and we know which voxels the beam has passed through. And thanks to that, at the voxel level, we can calculate the transmittance as the ratio between those beams that have passed through the voxel without having an impact and the number of incident beams in the voxel. So the only thing you should take care about in case of square voxels is that not all the beams, the path length in the voxel of all the beams is not exactly the same, and that may bias your estimation of transmittance. So there are different ways to solve it. My colleague Maxime Soma proposes to count only the beams that are crossing the horizontal cross-section, and in that case you will unbias your transmittance, and your estimation of transmittance will be robust enough. So, okay, from the LiDAR we can estimate total canopy transmittance if we take into account the number of beams above and below the canopy, but also we can if we work at the voxel level, we can describe very well the variability, the spatial variability of transmittance. This is an example on width where we can see the profile of the individual rows, and we can observe some problems of, well, some spatial heterogeneity. We will see later why. And also an example from my colleague Mario Seward on mice, where we can describe the variability of transmittance within the canopy. Another important trait that we can estimate thanks to the LiDAR is the vertical light attenuation in a canopy. This is an example from a LiDAR measurements in the experiment that I talked before. So we have at the heading stage 3 different cultivars with different, very different plant architecture. As we see, a genotype that is very planophile, especially in the top of the canopy. It intersects most of the incident radiation in the first centimeters, in the top layers of the canopy, which is a more erect genotypes permits the light to penetrate in the canopy. And this kind of vertical light attenuation profiles are very important for studies on photosynthesis at the canopy level, for instance, but also to characterize the inter-specific competitions with weeds, for instance, or with other species in crop mixture. So, okay, also transmittance is interesting, but thanks to the transmittance, we can estimate plant area, as we have, as Fred mentioned before. There is a physical model that relates transmittance with plant area. So it's the Beer is what is known as Beer-Lambert law. So there is a relationship between canopy transmittance, plant area, and this relationship is somehow shaped or influenced by average leaf angle. So if we would like to use canopy transmittance, we need to solve this equation with 2 unknowns. We need some information on the inclination of leaves. How to solve it? Well, a straightforward way is, well, we assume that we have a kind of good approximation to the average leaf angle. For instance, many people is using 60 degrees. And then the solution is analytic, is immediate. Another possible solution that we try to exploit with the LiDAR is using multiple observations of the same voxels. So as we have 3 LiDAR in the phenomobile, we have many voxels that are observed at 3 different angles. So having observations of transmittance at different angles make that this inversion is well posed, and therefore it can be inverted numerically to estimate at the same time the leaf area density and the average leaf area. Well, we tried to validate this hypothesis on this inversion. A first validation that we did is a validation in silico. So it was done simulating realistic width canopies using a structural plant model, a width model, and then we used the D3P platform from Xuyang to simulate LiDAR acquisitions in this virtual canopy. And knowing the true average leaf area, we can test our hypothesis depending on the voxel size. If we estimate total plant area index from the voxel, for aggregating the voxel's plant area density, or directly from total canopy transmittance, and the results indicate that, okay, from a theoretical point of view, in this kind of theoretical validation, working at the voxel level and then aggregating provides systematically better results, and also that the influence of the voxel size is important. The results are slightly better if we introduce some constraints in the average leaf area when inverting the Beer-Lambert law. we validated as well using in actual canopies. So this is the validation done thanks to our colleagues of Arvalis in Greux-les-Bains that you will visit hopefully on Friday, and also in the Diascope platform from INRAE we did some destructive measurements to validate the leaf area estimations, and the results are quite encouraging. Also on maize, so my colleague Mario Seward with the team of Arvalis at Montardon have also validated the estimation of plant area index, in this case leaf area index, on maize. And thanks to that, we can track time series of plant area density on different treatments. This is again an example on the experiment at Mogio at Diascope on last year. And what we can see, well, as we said before, these two cultivars have different dynamics on plant area density, so they have this confirms what we have observed with the canopy height, that they behave slightly different to a water stress episode. But more interesting is also how the different cultivars, the production of total plant area changes depending on the date of sowing on well water treatment. So we have some varieties where let's say the total plant area production doesn't change too much whether you sow in November or in January, but we have a more, let's say, alternative varieties that if we sow them later, they produce systematically plant area density. So also these kind of genotypic differences can be observed well with these dynamics of plant area density from LiDAR. And I would like to conclude my presentation with another example on, well, we can track very well the dynamics of plant area, but we can use also LiDAR to derive interesting information about the distribution, the spatial distribution, horizontally and vertical, of plant area. This is one of the first experiments that we did in 2019 at Toulouse, and it was an experiment to study the effect of plasticity of light competitions on wheat, and for that we remove from the microplots specific rows in order to create different neighborhoods, different distances between adjacent rows, and we wanted to know how the growth is impacted due to the different neighborhoods. So we had 5 cultivars, 3 durum wheats and 2 soft wheats, and we monitored it during time. So this is, for example, the profile of the microplot. We see the rows. This is mid-stem elongation phase, in the middle of stem elongation phase. And what we see from this graphical output is that the rows with neighbors more distant, they grow more, obviously, because they have less competition with the neighbors. This is the case of these rows that are alone or have only one close neighbor. What we didn't, this was expected, but what it was not so expected is this kind of structure that we call dominant subordinate. For instance, when we have 7 rows, we have the odd rows that grow more and even rows that grow less systematically in all of the genotypes. This is very interesting because it's actually a response to competition. It means that, okay, the first and the low and the last row, as they don't have close neighbors, they grow more. As they grow more, the second and the 6th row grow less. And as they grow less, the 3rd and the 5th grow more. So the fact that we have an odd number of rows in the group propagates this kind of heterogeneity from the borders of the microplot to the center. And this was something that we didn't expect. Actually, what is interesting is that structure are produced during tillering. I mean, if we made destructive measurements to understand which was the variable determining this variability between dominance and subordinating, and actually is the number of tillers, the density of tillers per linear meter what was produced. These were measurements at the BBCH 30, so the beginning of stem elongation. And tracking the early stages with an RGB camera, it shows that it's between BBCH 20 and BBCH 30 that the differences between the dominant and subordinate rows are established. So these are very early stage of development. So, okay, some conclusions of our work. So since 2018 and 2019, when we started to operate in collaboration with experimental units with PhenoMobile, we have progressed a lot. We have kind of operational modules in continuous validation, of course, for canopy height, canopy level, and voxel transmittance and plant area. Until now, most of what we do with LiDAR is based on statistical indicators, transmittance. We don't exploit still, but we expect to do so. Estimating, we have to understand how we can extract some traits like leaf inclination, organ detection, ratherly from the point cloud, from the surfaces described from the point cloud. We need to better understand the uncertainties in essential traits like PID, how to improve our estimations, especially to study how we can combine the estimations of some traits from LiDAR with other instruments in the PhenoMobile, like multispectral cameras, RGB cameras, and also from other vectors like drones. And last but not least, it has been mentioned before, how we can use this kind of dynamics of structural traits to understand canopy function, plant function in using models. We have some projects with labs and with experimental units on how to introduce these traits into crop models to understand functioning. And my last slide is to do some advertisement in this project, FAST, that we are trying to do so. We are recruiting a motivated two-year postdoc on deep learning and artificial intelligence to have some advanced phenotypic traits. The details are there, or just Google INRAE jobs phenotyping Avignon and you will find the job offer, or just contacted me on Sylvain. Thanks a lot.
Thank you, Raul. We have a bit of time for a couple of questions, if there's some questions.
Thank you, Raul. Have you compared the estimation of PID or reference index you get from the LiDAR with what you get from the RGB image using the method you have already validated at CAPTE?
We did kind of that comparison, but at the level of transmittance of gap fraction, not still with PID, but normally the model that we use is more or less the same. Well, with the LiDAR, we can estimate at the same time the PID and the average leaf area. And what we have observed in the synthetic validation is normally when we work with voxel transmittance rather to total transmittance, and this is what provides RGB camera, normally we have less scattering in our estimations because the saturation of canopy transmittance in dense canopies appears, and that produces a lot of variability of leaf area index. Whereas at voxel transmittance you have less saturation effect. You have, yes, some undersampling, problems of undersampling, but not light saturation. But this is okay, theoretical results. We should be a little bit more accurate than those methods based on total transmittance as RGB images.
But also early in the season, no?
Sorry?
you should also be more accurate early in the season when the leaf area index is really low and you have a strong row effect, no?
Well, early in the season, using the LiDAR for leaf area index or plant area density, on plant area index early in the season is a little bit tricky because the plants are already small, you have soil roughness, and you cannot differentiate well the impacts on vegetation and the impacts on soil. So this is probably there where we have to understand how to combine RGB, because in this early season, the segmentation of RGB images is much easier, yes.
Okay, I think we're running quite late on time, but if it's a very quick question, maybe we can.
Thank you. Have you looked at a larger number of different genotypes, kind of in the same, under the same conditions? And what kind of variation have you seen there?
Yes, I mean, so far, what we, you mean in the experiments on canopy height or on
the last one, basically, the PAD.
Okay, the distribution, okay, this, for that experiment, we had only a very small panel of 5 genotypes. It was very exploratory results, so we don't know how it will behave with a large number of genotypes. There are some differences in the response to but very subtle differences in the response of the distribution of plant area density light competition, but more or less the main features are stable among genotypes.
Okay, I think we should move on, and if someone has a question, can reach Raul during lunch. Thank you, Raul. I think our next presentation.
Good afternoon, everybody, at the CAPTE workshop. Unfortunately, I'm in the Netherlands, so I will give this talk online. For those who do not know me, I've got a few slides with me to introduce myself. So I'm Rick Van De Zedde. I work at Wageningen University in research, and my focus is completely on plant phenotyping in all different roles that are listed here. I have a background in AI, and I hope to inspire you and also to launch some nice discussions on research and development in phenotyping projects. So I've listed some information on our organization, but I think it's more interesting to jump to some ideas. So a few years ago, around 5 years ago, we actually launched an idea where we said, if we would like to measure plants, we need to know what kind of variety we are talking about, what kind of genotype, and we need to know the environment where the plant is growing. And if we know this, then we can actually measure the phenotype. And we said, but actually, if you want to scale up, you want to measure a lot of plants, you need tools. So we want to introduce data-driven plant science, as you could say. This is actually the argument that we use. So we would like to build a phenotyping center, which we call Netherlands Plant Eco-Phenotyping Center, NPEC, where we would like to know the parts of these equations. So we would like to test multiple genotypes in all kinds of environments and then measure the phenotype. So we need tools to measure the environment, and we need tools to measure the phenotype. Because I think that's the essential message that I would like to give to you. There are very smart people, you, others around the world, that are early adopters or even innovators in this domain. So they use technology for their specific research challenges, but there's a huge group actually of biologists and other profiles that could use these tools, but they don't have the access to the very advanced, complicated technologies to study the phenotype in detailed levels. So what I think at this moment that we are actually still having this gap. So we are, and that's what we use also for NPEC. We said we need to have tools, not to give this to the early adopters and the innovators, but to give tools to this early majority, late majority group of people that could then study their plants to find varieties that are very robust in this changing climate, and then phenotyping tools can really have an impact on the food supply of the world, for instance. If we talk about drought developments worldwide, we need to find crops, varieties that are very drought tolerant. So we need to run a massive amount of experiments to find them, actually. But those should not be done by the technology developers. Those should be done by the breeders. So those arguments we used to launch NPEC, and our Dutch science organization gave us the money to build a research center. So we received the money actually to build the center. So it's not a research project, but really a construction and development project. And we are open for access. So if you would like to use the tools that I will show in the upcoming slides, you're welcome to ask for access. And the official opening of NPEC will happen this year in the Netherlands on the 26th of September. So the essence of NPEC is that we have modules that focus on specific challenges, 6 modules and a data module, actually. And I will dive deeply into the greenhouse module and the open field module, because those two have been operational for the last 1.5 years. And the others are actually being constructed, being finalized as we speak. So let's dive into the greenhouse module. So we have a greenhouse, and it's packed with sensors to measure the environment and imaging systems to study the phenotype. And basically we have 2 ideas. One is bringing plants to imaging stations to capture good quality data. But if you move the plants, you introduce some growth effects. So we also have plants growing on tables, and sensors move to those plants. And I'll show you only a few examples, but this is just a picture of a tomato experiment. These tomatoes travel to imaging stations. They get imaged one by one. So the plants need to travel to be imaged. Also, the plants need to be traveling to get water. So it's a conveyor-based system. And we have got multiple imaging boxes here to capture the phenotype with different camera systems. And just to make it very obvious, so we are collecting hundreds, 1,000, 1,200 plants over time. And then we are accumulating data, massive amounts of data, so pictures of plants each day. And already to show you some insight that we collected, if we give this raw data, just the images, to the end users, the biologists, they are not able to extract information from these plants. So we have been developing Python code. We have been developing all kinds of visualization tools like this one to show how the data looks like. So for instance, in this phase, we've very simple Python code that simply calculates information out of the data. So plant height, plant width, estimated biomass, like the compactness of the plant, and a lot of other vision parameters, just to give biologists information instead of overloading them with data. Because all these systems produce data. So the first step was actually, let's make sure that all the PCs that are connected to cameras, either on the drone or in the greenhouse, in the climate rooms, are getting rid of their data. So they're uploading their data to a cloud. So there the data is piled up. So we are organizing the data. So we make sure that all the metadata is in place, but maybe some error logging is in place, or settings of cameras are there. And our next step is actually, we help the users to analyze the data, and we help them too by visualizing some parts of the data to make sure that they dive into the data, get a grip of what's in there, and then start digging and extract those bits and pieces that are relevant for their specific experiment. And our end users log into the cloud to find the bits and pieces that we have put there ready for them. And there we are using a tool called iRods to organize the files. And we are implementing FIS from INRA to extract information. So say bulk data goes into iRods, information goes into FIS. And one concern actually that we have is that metadata is crucial, But our users are not so motivated to capture all the existing metadata. So what we actually have as a principle, the guideline is NPEC will store the metadata for its users, because often the metadata questions come 6 months after the experiment. And then they ask, okay, what was actually the watering regime? What was actually the temperature that day, etc., etc. So just to inspire you, I would like to show you one specific experiment that we have been working on in the greenhouse. It's an idea that we have, on the one hand, sensors, different genotypes, and cameras on a real crop, while in the same moment we are developing a greenhouse, a virtual greenhouse. So we have a greenhouse model, a plant growth model in place, and we are trying to align this on such a detailed level that actually if you would look at the virtual plants, it will really resemble the physical, the real plant. So the digital twin has a physical and a virtual component. And if we are able to grow plants identically in both situations, we could also run different scenarios in the virtual domain and look at the phenotype that will be developed in lower light conditions, different varieties, other types of greenhouses, different cropping system, etc. And we could work slowly towards a fully autonomous greenhouse where the grower can run scenarios on his crops without doing it actually in real. Now we have been quite busy in developing, on the one hand, the system, the phenotyping system where the tomatoes are running around, while also developing a similar feeling actually on the virtual version of the greenhouse. So this is the digital twin experiment. So you can see some tomatoes growing here. Actually, the gaps are here because we are doing destructive harvest to collect reference data for the measurements. And actually what is crucial in plant growth is actually light. So the light that shines onto the plant is the key to actually predicting growth. So if you can measure the light quality and the light intensity, you can also predict how these plants will develop, how fast they will actually grow in time. So just to show you one example actually of the current status of a fully implemented version of our greenhouse. So this is actually how the greenhouse looks like. This is the sun traveling over the plants. So you're going to see all kinds of shadings and effects. And the model, actually, we can also work on the virtual model, how it grows over time. You could walk around in the greenhouse, so you get a bit of an impression. And we are tuning now the models, the virtual plant models, so they resemble really the different varieties. While taking also into account, for instance, the amount of light that was really entering the greenhouse. Parts of the light was absorbed by the glass, part was, for instance, because of the canopy interaction, blocked by other plants if they get too tall. And if this really works, then we can also show this to growers and say, okay, this is the virtual version of the greenhouse. How would that work for your situation, and how would that help you in optimizing actually your the growth of your tomatoes in your greenhouse? But let's dive also to the field, because we've been doing several experiments there also in the last 2 years. What we basically said, we need to have mobile systems. So we need to have systems that travel to the plants where they grow, either in soil or clay soil or in sandy soils. And then the essence is, again, that we have been developing this for years, but we would like to have now tools that we can give to biologists. So the essence is actually we fly on a field, for instance, with a drone, equipped with multiple cameras, or we drive on the field with a vehicle that is actually an imaging box on wheels, and it's collecting data based on actually predefined locations where plants grow. So we talk about plots. Each plot is a specific location in the field where during planting already specific varieties have been planted or specific treatments are scheduled. And as well, the drone, as the trait seeker, report back based on these plot definitions. But I think what's more interesting also to show is that we have been doing this for maybe 20 years. And there was one specific example of a disease detection project on potato fields done by my colleague Gerrit Polder. And he has been using hyperspectral imaging to find early disease symptoms in potato plants using actually deep learning. So there is we have implemented actually a neural network to link, based on the hyperspectral data collected by his prototype, a signal basically that mimics exactly what the expert is actually telling the system to do. So we have a target that is actually on this ridge of potato plants. Where are the diseased plants? Where are the healthy plants? And the neural network is just mimicking this human expert. So, and we publish this data, and then actually the research basically stopped. But then if a grower or a farmer would come and say, I would like to use this tool, then the prototype was not available anymore. The cameras were used elsewhere, but the data set was still there, and the publication is still there. But actually there is also exactly there where NPEC comes in. So we said, we will have this prototype, as you'll see on the picture, ready for other researchers, other companies that would like to do this again. So there actually the trait seeker comes in. Just to show you a picture, so it's a device on wheels. It's actually quite similar to the prototype that Gerrit developed a few years ago. So it's a box on wheels. It has all kinds of sensors, cameras here. It has RGB camera, 3D LiDAR. It has hyperspectral cameras. It is plot-based, as I told you. So as soon as the system enters a plot, it starts recording on that, basically on that tag. Driving the machine is quite easy because it has AB line driving and cruise control. So if you're actually driving at that moment, you don't need to look where you're going. And by defining these plots, we can also link the data automatically to drones that fly over the same field, which then have a larger range, for instance. So just to show you some insights, so if the drone flies over a field, you can capture large areas. But if you would dive in more detail into the specifics of, for instance, these lettuce plants, then maybe you would like to measure very specific aspects on shape. So then you have the 3D LiDAR file. Or maybe you would like to combine actually your NDVI picture from the drone to the trait seeker, but at least the data is fused together. So on the same plots, you can get the same data with different modalities. So just some specs. So the trait seeker is a machine that you can book basically as a researcher company. Plot needs to be around 1.5 meter. It has this AB line driving. So we actually go to your field. We drive with the vehicle and we give you the data. So it's captured data based on plot polygons. There are all kinds of smart tooling in there to get good quality data. So the sensor data is geo-referenced for location, but also with the GPS INS. So if it's a bit of wobbly field, it is compensating actually this wobbling. So the data is much more stable than you would expect if you would have a wobbling camera on your field. All the sensors are fused together on pixel level. So each pixel has 3D, RGB, and also hyperspectral data on top of each other. So that makes the analysis very interesting. We have two hyperspectral cameras in there. It's an FX10 and FX17 from Spectrum. It's a SICK LiDAR sensor and a high resolution RGB camera. And just to show you how it looks like, this was a field trial that we've been working on last year quite intensely. Lettuce collection with all kinds of variety. Quite some breeding companies are involved. This is my colleague Peter, driving the machine. As you can see, he doesn't need to steer, he doesn't need to the control procedures, just checking if everything is working fine. Data is collected on the PCs, and as soon as the machine is ready, data is uploaded to the cloud for further processing. You can see it has an active light source. The stable light conditions throughout the And just some ideas on metadata. It's very, very straightforward actually, but there's all kinds of MAPI inspired data also linked to the imaging data. So we get environmental sensors on the system that are being collected as the machine drives. In the same time, we have all kinds of metadata on the specific location of these plots. But also plot names, but also event names, or also how the machine is entering this particular plot is all recorded, and it makes life easy when you're diving into the data later on. So we got all the metadata on the settings of the specific cameras are in there, and this is just piling up. We add it to the data when we hand it out to the researchers. So of course, there is much more to tell, but I was restricted in time to keep it within 20 minutes. But you can come over to Wageningen on the 26th to the 30th of September. We will give live demos. We will have great talks. So I hope I will see you there. So summing up what we are doing, so we would like to measure, understand, and predict plant quality in climate rooms, in greenhouses and fields. So I'm quite focused on launching new research projects, probably also with several of you listening to my talk. And we are providing access. If you would like to use some of our tools that I showed, you're very welcome to come over. And we are still exploring the potential of this large-scale research infrastructure, not only in the Netherlands, but also on a European scale with emphasis, or on an international scale through the International Plant Phenotyping Network. So I would like to thank you, and if you have questions, I'll be available live. I hope you can hear me. Now it's live. The other one was a recording. Yeah.
Okay, now it's working. Thank you, Rick. We may have time for one quick question, I guess. So, but it has to be really quick because otherwise we miss out lunch. Any question?
Yeah, that's bad, I would say.
Yes.
I don't hear anything. Right?
Sorry.
Hey, Rick. Thank you very much for your nice presentation. So I was kind of wondering, you presented a virtual greenhouse, but those plants are not look very real. So I was wondering how you made those virtual plants inside the greenhouse.
Yeah, those virtual plants are developed as FSPM models. So they are based on a plant model, which are actually, as we speak, currently being tuned to fit the different varieties that we have been testing. So this is the virtual tomato crop experiment, and the model needs to respond to changing conditions. So it's not so much as making the plant look as close to reality as possible, it's also to make the plant respond to reality. So if we change the input of the light, then the plant shape needs to change. And that's the crucial aspect. We had another idea, actually in one of my slides I showed also a 3D model scan from a tomato plant, and then it looks real, but then that particular plant doesn't respond to changes. And we are looking really, that's the key element of the digital twin. If you change your settings in the real world, your virtual version needs to change accordingly. If that happens, then you can rely on your virtual version of your digital twin. Hopefully that answered your question. There will be a publication actually coming on this project later this year.
Excellent. Thank you. We should move to the next speaker, that I think is
Thank
François.
you. Yeah, have a nice day. Have a nice lunch, everybody.
Thank you, Rick. It's a pity you
sorry
missed the
I'm not
lunch.
there.
So now the pressure goes on François to finish on time so we can get some lunch.
Can I have the presentation? Yeah, great. Okay, so to finish the morning, although we are in a session for field phenotyping, I was asked to discuss a little bit what can we do with the indoor phenotyping in this context. So you know that phenotyping began with the indoor, mainly with the phenotyping platforms. And now that the field phenotyping exists, so one can honestly wonder whether indoor phenotyping is still worthwhile. And to be honest, the conventional wisdom for many people is that we should just close the indoor platforms. So for some reason I don't agree, but I have a conflict of interest. So I would like to share with you some ideas of what are the ecological niche of indoor phenotyping that will never replace, of course, field phenotyping. So part of this is in the French infrastructure phenome. So we have seen several of those field equipment in earlier presentation, and I will show a little bit of equipment and result in control conditions. So the question is what to measure, and it is common to field and indoor. We are interested in physiological mechanisms, but genetics needs hundreds of genotypes. And when I say hundreds, now it's more 300 than less. So we need really, if we want to do physiology with genetics, we need physiology at a high throughput. So some things are possible in the field, perhaps some are not, and we'll discuss that. And another question, and sometimes the two questions are mixed. So to what extent are these physiological traits related to field, to yield? But this is a different question, actually. So when we see the whole range of phenotyping, we have a phenotyping in the physiology community, basically at the cell and level of square centimeter over minutes. We have seen quite a few FSPM at organ or plant or canopy levels. We have not seen yet multi-environment field network that are key to understand the base of yield. So what I will do today, what complicates that is that the time and the variation of environmental conditions is blurring everything. So it's blurring things at this scale. So for instance, the water potential is quite high in the morning, low in the afternoon, light is the same. So every measurement that we make during one day will be different in 2 minutes. So this is a major problem. But we are not at all better in network of field experiment. These are different years, and it's in the same site, in the same field. And one field this year can be quite dry, it can be wet. We are in Avignon. If I do an experiment this year, I have no clue whether the climate will be dry or wet. And more often than not, if I do a dry experiment in Avignon, it will rain the whole season, because such is life. So the confusions of effects at all these scales are due to the variation of environmental conditions. Okay, so physiological mechanisms and gene networks work over minutes, yield over months, with a huge variation of environmental conditions. So what I will do in the rest of this presentation is comparing these two levels and seeing to what extent measurement at plant or canopy levels, mainly in control conditions, can inform about yield in a network of field experiments. So for that, one word about the phenotyping platform we have in Phenomemphasis. So we have a phenotyping platform in for leaves, one for roots in Dijon. There are others in Angers and Toulouse that are basically on this. So we have 3D analysis of plants. So the interesting thing is that plants are in canopy, but we can, because they move, we can still have the architecture of individual plants. And usually what we do is from these individual plants, we reconstruct virtual canopies and do quite a lot of calculations based on these virtual canopies. And I will show some of it. Allez? Okay. So the question is, in fact, the question I'm asked whenever I present data from indoor platform is to what extent traits in a platform translate to field. And it's important to say that by default, they don't. So probably the best way of spending public money without any interest is to measure yield in the platform. So this has probably no sense. So a phenotyping platform is not for that, except in very special conditions. I don't, but usually it's not. But I will try to show that yes, they can provide important information that relate to field, provided that precaution is taken. So I want to begin with the two traits that are absolutely crucial for modeling. So one of my points during this presentation is that platform experiments are basically for doing modeling. So a precise idea of phenology and a precise idea of response curve. So how is the response of leaf growth rate to air drought VPD for the believers. So here I present two experiments in the field, 3 in the platform, and you can see that if I express things as a function of thermal time, then it's exactly the same in the platform and in the greenhouse. Except that it's much easier to do that in the greenhouse. To my knowledge, we cannot count things in field yet. And this is just impossible to do in the field. I had some field points once in my life, and I will never do that again, because this is having displacement transducers in the field, and this is far from straightforward. So we can see that for these two, we have a common behavior for field and platforms. If we believe that, then we can have the genetic variability. So now we have 250 genotypes here. And the progression of phenology, we have it for all the guys that are here, but I can trust that it is usable in the field, provided that you use thermal time and not common time. And the response of water deficit, you can see that we can identify very different responses. Some genotypes stop growth at a VPD of 2, some continue afterwards. And this is heritable, this can be used, and it's something you hardly can have in the field, at least today. So we can do genetics out of that and use it in further model, even with genomic prediction. A second thing I want to present is light interception and radiation use efficiency. So we have seen quite a few applications in the field, and they work quite well. So, but it can be done also in control conditions. So we have our individual plants. We have a 3D reconstruction for that. So it's the famous digital twins. So we have a twin every day for every plant, and we can reconstruct every day the canopy and do a lot of calculation out of that. So, allez. Okay, one of our favorite traits is RH pad, which is from the top of the canopy, the place where half of the leaf area is located. So if you have a high RH pad, it means that most of your foliage is here, and otherwise it's here. Something that we have seen that we can perfectly do in the field as well. The interesting thing, apparently this doesn't work. Okay, in this direction. Good point. So here I have a panel of genotypes. This is a year of release. So these are all genotypes. These are recent genotype, commercialized. And you can see that breeders select for yield, but indirectly they selected for plant architecture. So in this panel of genotypes, either in water deficit or in well-watered, this trait was selected. So if this trait was selected, it means, one, that we measure something that is valid, and second, that this trait is probably quite important. And actually in another panel of diversity, this trait is quite well related, genetically related with yield. But the important thing in the context of today is that we heard about the average leaf angle in former presentations. If I relate in the same set of genotypes, but this is RH paired like here, okay? So this is what was here. And this is the ALA with drones with the same genotypes, but in the field. And you can see that the square R is quite good. So by measuring in the platform, we can have a quite good idea of what is happening in the field. So again, in the platform, I can have good information. But you can see, okay, but if we can have it in the field, what is the interest of having it in a platform as well? And this is straightforward. Well, first, when I showed this result to Fred, he was relatively relieved, because this is model inversion, and you have seen Fred's presentation, so when we have model inversion, sometimes we're not so confident. So this is the first interest, but perhaps we could do that 3 times and it will be finished afterwards. For me, the main interest is testing as many combinations of events as you like. So many genotypes, combination of species, etc. So the specific advantage of this approach, that is not exclusive of a field approach, of course, is that you can have the radiation interception efficiency for any canopy that mixes varieties, species, everything you like at different densities, different plant organization. Doing that experimentally take ages. It still needs to be done, of course, but you can test many possibilities and optimize things and test in the field the most interesting possibilities. And from the platform, you can have radiation use efficiency with a good heritability, so you can have genotypic dissection, etc. So until now, I showed that no, I will. some traits can translate from the platform to the field. I want to show a couple of cases where they don't, but we can understand what happens. So if I take leaf width, so we know that in monocots, if you have low light, you will have very thin leaves, and it will be larger. So if we take the plant in the platform, they have a width that is much lower than in the field. But now, if you look at the field, there is a huge variability also. And if we express everything as a function of intercepted light, then it makes sense. And the platform is not different because it's a platform. The platform is different because there is lower light. So there is the possibility of having more light in the platform, or at least you understand what happens and you can try to see what will happen elsewhere. It's the same for leaf length that responds a lot to air drought, or VPD. And you have a huge variability in the field as well, and the platform that fits in the general regression. So in this case, you can say, okay, platform or field are different, that's fine, but they are different because of causes that are common with the variability in the field. So then we can begin to reason. And the last example I want to show is tomatal conductance, something that by no means you can measure in the field. You can measure with the gas exchange, but believe me, I've tried. Trying to have 300 genotype with the gas exchange is somewhat challenging, and and Romain is here, and we took the whole data set and put in the dustbin because it was absolutely worthless and it was a lot of work. So we imagine a way to have that, and that is the Penman-Monteith equation for the believers, relates the flux with the environmental conditions plus tomatal conductance. So if you have the flux, if you have, by weighing, if you have the environmental condition, then you can calculate stomatal conductance. And actually, it's not bad. If we take only well water, and this is the genetic variability, we have a square R of about half, meaning that we express half of the genetic variability with this method, knowing that we also have an error on the gas exchange. So it is usable. If it is usable, again, we can have a genetic dissection, and we tried even to have a genomic prediction on that. So if we know genotypes only with the markers, again, these are 250 genotypes, so it's a high throughput thing. But if we have only the genomic information, we can still predict more or less, not great, but some of that, we can predict stomatal conductance. So in these in these examples, I wanted to show that if we are careful, we can get information. I had, okay. Okay, let's go very quickly to another question. To what extent, so I tried to show that the traits in the platform can represent something in the field. Now, are they linked to yield? And more often than not, I'm said they are not linked to yield. Okay, so what? Because in fact, the alleles are more often than not are conditional. Allele effect. So we have here a lot of experiments, different yields, and in fact, we had, when we did the QTLs of yield, we had more than 600 QTL that moved all over the place. But now, if we group all these experiments by environmental scenarios, and I will not explain exactly what the scenario experiment, but you can believe that some fields are are drier, some fields are hotter, etc. We group them. So this QTL here is negative in severe water deficit. It's positive in mild conditions, etc. So our traits will never directly correlate with the yield, but it can correlate with the yield in some scenarios. And what is true for one QTL is true for many QTLs, and now we are trying, and I will not present that today, but to link traits to yield, but to yield in one scenario, not in every scenario, and it works relatively well, quite well actually. Okay, so the conclusion for now is that platforms do not represent the field, but one field does not represent another field either. So the role of indoor phenotyping is to have better explanation of what happens in multi-site field experiment grouped in environmental scenarios. So I want to very quickly show how this can be combined for predicting yield. So these are two relatively recent papers. So we can, from our data, and I've shown that, do a genomic prediction of phenology, or directly do that in the platform. Then if we have that in the platform, then we can calculate the real phenology in every site because we have the environment. And if we are too lazy to have the environment, we can use environmental grids. Then we can use models, but it's not FSPN models, but crop models that predict what happens for yield. For instance, we can see that in experiments, if we have cycle duration, there is an optimum. We have the same optimum. We can see the optimum in a crop model as well. And so we can predict yield in many places as a function of the optimum in current climate and in future climate. And the conclusion of that was that based on all this combination of methods, genetics plus modeling, in current models of IPCC, the yield decreases with the climate change, but this is assuming that the genotype will be the same. If we assume now that there will be, that farmers, and they do that, remain at the optimum in 50, then the yield can be maintained or slightly increased. Okay, so conclusions. It is a multi-scale problem, so we need multi-scale solutions. I think that the opposition between field and indoor phenotyping makes no sense, but we still have to find the ecological niche of each of those. So for physiological mechanism in precision platform, I think the mantra of my presentation, this is basically for modeling. So the result in a phenotyping platform makes no particular interest. But if you use all the parameters, genotypic parameters, 200 or 300 genotypic parameters, then you can use it in models and derive many results. So the high throughput is, of course, essential. If we want to see field, then we need to go to the yield. We need to go to the field and see where the alleles are favorable. So it's difficult to disentangle environmental effects. So here come the physiological mechanism and modeling. And as I said, some traits are impossible to measure in the field. So I think the future is develop of method to link phenotyping scales and include them in genomic prediction and in modeling. And I think if we can do that, we will progress together. Thank you.
Thank you, Francois. We may have time for a very quick question, please. Better. Thanks. Can you hear me now?
Yeah.
Okay. Yeah, coming back to Fred's presentation or linking the YouTube presentation, you think that some of the traits like
final leaf length that you showed the response to VPD. Okay, you cannot measure it in the field, but do you think that using a model...
Sorry,
do you think that using a crop model, for example, or any model, you can invert your model and estimate the sensitivity to VPD, for example? I mean, do you have a reflection on that?
The short answer is, I think yes. If I want to consider the maize, the sorghum, the sunflower, if it is to infer genotypic differences that can be quite small, and infer the difference in yield between genotypes, to be honest, I don't believe that too much.
Thank you. Yeah, Alexis.
No. Yeah, thank you. May I just have a small question regarding scale? Because from what I've seen on most phenotyping in the field, you can have 10,000, 20,000 plots, so modalities that you try a little bit more massively that you cannot really do in the greenhouses because you're limited to 2,000, 3,000 pots generally. So the scale is not the same often. And I don't really understand how you... I mean, it's a question for you actually. Today, field phenotyping is improving every day, and basically tomorrow it will be even more precise than yesterday. We will scale much more in the field than in the greenhouse. So it's just very. So what is left for greenhouse phenotyping then? I didn't understood very well.
I tried to answer this question. So basically, if I summarize what I say, do in the phenotyping platform what you cannot do in the field. So that's the first question. Second, we can disentangle things sometimes, and I have worked a lot in the field, so I'm not defending one versus the other. It's very difficult to disentangle the genotypic effect from the environmental effect. For instance, one genotype is larger, so it dries more the soil than the small one, and there were many of those for drought tolerance. You end up saying that the small genotypes are drought resistant, etc. So the phenotyping platform is also to disentangle things. Then the 2,000, for you need reps, but you can repeat the things in the platform perhaps more than in the field. Again, I'm not discussing that field phenotyping is necessary. I'm saying that if we have the field phenotyping, we still need to have these big experiments across Europe. It's not 3 field phenotyping that will give anything, I think. And then I think the platform experiment combined with modeling and combined with the genomic prediction will give a lot of information for better interpreting the field results. That's my best answer.
Okay, thank you, François. I think we'll close this very interesting session. So thanks from José to help chairing the session.